co-chair of the Land Ice Working Group, and will be co-hosting a meeting along with Jan Lennertz, the other co-chair, and liaisons Gunter Legee and Kate Thayer-Calder. So before we get started, well, first I wanted to acknowledge Elizabeth Faircloth, who's been planning this working group meeting as well as all the other working group meetings. And we're now on the last day of the last meeting, and my experience is everything has gone incredibly smoothly. So big thanks to Elizabeth for pulling that together. For the talks, yes, applause, thanks. For the talks today, we have a 15-minute talk AGU style, but we will not be pulling out the yellow light and the red light at 12 minutes. We have had speakers take the full 15 minutes, and that's okay. If so, we'll just put questions in the chat for after the talk. But if you finish before 15 minutes, that's great too. And then we'll have time for a couple of questions. And so this is the land ice focus session, the last session of the 3-day meeting. Our formal talks wrap up at 11:30, and then we'll have time for discussion if people would like to stay and discuss anything up until formal adjournment at noon. So we're going to start off with quick updates from me and from Gunter and Kate. I believe Kate's going to lead off. So Kate, if you'd like to go ahead and share your screen. Is your share screen button working, Kate?
Okay, so yes, but apparently my computer needs permissions. Here it goes.
Okay.
Apologies. I have a new OS on here. Okay. So I won't be able to record the contents of my screen until it is quit. So I'm not sure what that means.
I think you need to restart Zoom. Kate, I'm afraid, but let's try. What happens if you just now share your screen, because we can see your screen? So
my screen, okay.
Yeah, it looks like it is working.
Okay.
Let's see.
Wait, done.
That's the wrong kind of share.
Wrong kind of share. Here it is.
Great. Yeah,
that looks great.
I'll do this, and we'll see what happens with the recording later. All right, good morning, everybody. I'm Kate Thayer-Calder. I am the software engineering liaison for the Land Ice Working Group. Thanks for joining us this morning. I'm going to be giving sort of a software engineering update on how CESM and CESM have progressed over the last year, and a few notes on CESM in general and the computing system here at NCAR in general. So a quick overview of what the three of us are going to cover this morning. I'm going to be doing a little bit of software engineering focused updates. Gunter's got some activities to talk about, and Bill Lipscomb is going to cover the code towards the CESM 3 release, hopefully later this year. So just some updates from the computing environment here at NCAR. We have a new supercomputer that's set to be delivered this summer. It'll be first available for people who have the ASD proposals. So they sort of do a test bed for the new computer, and then available to the full community next spring. So after about 6 months of test work from the groups here at NCAR. This machine's named Derecho, which is a type of very severe storm that can form on the Rockies in the Central Plains of the United States and travel eastward with high winds, hail, lightning, a lot of exciting storm things. It is a nearly 20 petaflop machine that when we bought it was a Cray machine, but then HP bought Cray, so now it's an HP Cray machine. And you can actually test it if you want to with your software right now. There is a container with the environment available using all the Cray compilers and the Cray OS. So if you're interested in that, there's a link here and you can read more about how to get on and give it a try. There have been no major CESM releases in the last year. So I've noticed in my past winter meeting updates that I talk about CESM releases, and this year has been a lot of work towards CESM 3. So there's been a whole lot of science updates and a whole lot of beta tags, but no official releases this year. Many of the components are currently in development and some scientific flux. So if you're using the recent beta tags, you can get the latest and greatest, but you're not going to be using the most scientifically validated code at this point. But one of the cool things that recently happened is that CESM now supports the new NUOPSI CMEPS coupling framework, which is a whole rewrite of the guts of CESM. Done by Mariana Vertenstein and a bunch of ESMF people here at NCAR, and it's going to be allowing all sorts of new and exciting capabilities in CESM going forward. One of the things I wanted to note is that there have been a lot of changes to Python on Cheyenne in the last few months, and I think that they're trying to produce a stable and useful environment for everybody, but that's caused some differences in workflows going forward. So CESL moved the Python environments and executables into a supported Conda module. It used to be that you had to actually install Conda in your home directory and run it from your own executable. Now there's a module that you can load, and that includes all of the NCAR Python libraries, the NPL. So once you load the Conda module, you will get the NPL and a bunch of other NCAR commonly used libraries with it. And there's good documentation on that at this length, which I think everybody should check out, because this Conda module and the NPL will be updated at the start of each month. So CESL is doing a great job of staying on top of all of the Python versioning and updating and library changes as they come along. CESM itself is moving away from Python 2 and standalone testing, thanks to a lot of work from Gunter. So it will soon require Python 3 to do standalone test scripts if you check out the head of the branch, and probably set in CESM 3 going forward. And then just some gotchas that we've seen recently. If you want to invoke Python 3 in a script on Cheyenne at this point, you need to specify the executable Python 3. Just saying Python won't give you the Python version that you have loaded, which is a little funny, but that's the way it's working right now. You can't run MPI run and MPI exe on the command line anymore. You definitely need to start an interactive node in order to use those commands, which is good for performance on the machine. And then, as usual, make sure all of your module versions match. So when you build code, you want to make sure you're running with the same version of the compiler when you actually run that code, or you're going to get all kinds of weird errors that don't make a lot of sense to people. One of the big software engineering tasks this year has been done by Bill Sachs. He finished all of the work required to support multiple active ice sheets in CESM. So now you can run with Greenland or Antarctica active in CESM, or both. Which is really cool. And this was supported by the new NUOPSI changes and the way that NUOPSI handles grids, which is much more flexible than MCT originally. So now we've made some changes to the comp sets. When you load CESM comp sets, you have to specify which ice sheet you want and then what status for that ice sheet you want. So you'll see in the comp set name CESM2, Antarctic ice sheet evolve, Greenland ice sheet evolve. So you're specifying which ice sheet and what mode you want to see it in. You can do that in a short name by saying G for an active ice sheet and little a for Antarctica, or little g for Greenland, or little ag for both. So you get the new GAG comp set, which I think is pretty fun. And then you'll have to have a grid specified for each of these. So the Greenland ice sheet, instead of being the GL4, we have it a little more specific GRIS, and the Antarctic ice sheet AIS. So there's a lot of documentation with these updates is available as well. Everybody should check that out if they're interested in trying this out. This is a new capability, but we're interested in having people give it a spin and see how they like it. So let us know if you encounter any surprises or issues as you're using this new capability. One of the big things that I've been working on this year is a collaboration with GHub, which is a website bringing together modeling data, observational data, and all sorts of ice sheet tools and data sets available. You can check it out at this link here, the ghub.org. It is still in early stages, so we're working out a few wrinkles here and there, but it offers currently from NCAR a few data sets from our ISMIT coupled CESM runs, that you can use to force regional models, and then a Python notebook tool for visualizing the surface temperature in those data sets. In order to see our data sets or any other data sets on there, or to use the tools, you will need a free account. So you'll sign up, and then you can have access to all of the cool stuff on there. So definitely check this out, because I think it's going to be a really great resource going forward for the entire ice sheet community. So that's all I've got. I'm going to let Gunter or Bill take over. Actually, nobody was clear to me who's going next. I'll stop sharing my screen.
I'll take over.
Awesome. Thank you.
Hopefully you see this now. And... all right. Does everything look okay to you guys? All right. So I will continue what Kate has started by giving you some updates about our activities. First, I'm going to tell you a little bit more about what's going to happen for the new releases of CESM. First, there's going to be most likely a CESM 2 question mark. We need to figure out the number here before CESM 3 comes to play, with new initial data set, new test cases for CESM, new physics that Bill is going to talk about, new capabilities for glaciers that Bill will also talk about, and the move to Python 3 that Kate just highlighted. And for information, I wrote a quick Google Doc here on the do's and don'ts with the new Python 3 environment within Cheyenne that the Lenders Working Group folks can access via the Google Drive. So new initial data set for Intellicar. First, we're going to have a new geothermal heat flux. We used to use a Shapiro and Ritzvoller data set from 2004. We're moving towards the Matos in all 2017. And you can see here in those black boxes that the main changes are more on the west side of the Antarctic ice sheet, in the Antarctic Peninsula, the Mary Birdland, and the Northwest Ross over floating ice here. And these fluxes are more than double what we used to see in the older data set. So we'll see what changes that will lead for Antarctic spin-up and forward simulation. Intellicar again, we updated the new bed machine version 2 from Matthew Morningham. There was a version in 2019 that we used to use. Now there's a new data set that's available at NSIDC in 2020. And the main changes you can see in this black box in bed topography here, there's a bigger difference in which the bed topography in 2020 is much lower in this black box area, and which means also a difference in thicknesses. On the Greenland side, we're also updating the geothermal heat flux, also moving from Shapiro and Ritzvoller to Matos. And you can see here, overall, the larger heat flux in the new data set and improved structured compared to a more uniform structured in Shapiro. And what the black box that I'm highlighting here, we've had a lot of trouble within CESM to actually reproduce the northeastern Greenland ice sheet glacier. And we hope that this new data set will help a little bit with this by improving the basal water underneath the ice. In Greenland as well, we're going to try to use the more regional climate model as opposed to the RACMO one. One of the reasons for this is that MAR provides us with near surface temperature vertical gradient and surface mass balance vertical gradient. And also some surface mass balance outside of the initial ice sheet mask. It's a bit funky, but it is what it is. And also gives us some improved process resolution in glacier region that I highlighted in the black box. There's a bit more structure there. So hopefully with some of these changes, let's cross our fingers and some good vibes, all of our CESM inversion will be resolved, right? So let's hope for the best. The new test cases, and let's see if I can, okay, it plays on its own, so that we're going to add a more continental scale test cases. And for Intellicar, it's going to be at 8 kilometers, for Greenland at 4 kilometers. And for both, we're going to set up some spin-up examples that the user can run and get familiarized with the process of running spin-ups. On the Antarctic side, we're going to add the ABU-MIP experiment, which stands for Antarctic Buttressing Model Intercomparison Project, which was done in 2018 by Frank Patin and Sonny, I forgot her last name, I'm sorry. The principle of these experiments is that ABUM induce extreme subshelf melt under floating ice, which leads to a large ice retreat that you can see on the left-hand side of this movie. And ABU pretty much removes every single floating ice that gets formed that you can see on the right side of the movie here. And it could be used somewhat as a benchmark because the sea level rise that you get with the ABUM experiment should always be less or equal to the one that you get with the ABUC experiment. So if you change your physics in CESM and you don't get these relationships, then something might be iffy. On the Greenland ice sheet side, we're going to add the init-MIP experiment. So init-MIP was a precursor to the ice sheet model intercomparison 6, which was the ice sheet part of the CMIP 6 experiment, which prescribes schematic surface mass balance anomalies. So the goal for this test case is to introduce users to continual ice sheet simulation, but also run for a few years on any platform, even on your Mac. Moving toward more activities, so as I was mentioning, ISMIP 6 used to be the ice sheet component for CMIP 6, but it only ran until 2100. And previous studies, including the one from Lipscomb and Lowe in all 2021, showed that a lot of interesting physics happens after 2100. And so there's a proposal to extend these experiments until 2300. And to do this, they're providing extended forcing for thermal forcing anomaly and surface mass balance anomaly from 6 global climate models, including CESM2, which was rerun using Wacom instead of CAM. It's going to lead to high and low emission scenarios from CMIP 6 and CMIP 5. And you can see on the left-hand side here, the mean surface mass balance anomaly. And at 2100, you can see that some of the models started to give some interesting response, but it kind of ramped down much faster after that time. So where the interesting things take place, you can see CSM2 leads to the largest anomaly up to minus 700 millimeters per year in surface mass balance anomaly. On the right-hand side, you can see the difference on the surface mass balance between 2300 and 2015 that leads very different patterns depending on the model you're using, with UKESM and CSM2 showing the strongest differences. So our plan for this is to extend the run we previously submitted to ISMIP 6 and set up and run new simulation using new initial data set, updated physics, and spin-up techniques. A new initiative that started, calving MIP, which stands for Calving Model Intercomparison Project, it's at its early stage development. We had a first meeting last week. It's led by Jim Jordan and Frank Patin from University Libre de Bruxelles and Hilmar Gudmundsson in Northumbria University. And they're proposing 4 design principles, more like idealized test cases with a flow band and an idealized bed to test the numerics of the models, and 2 more realistic geometries with regional and large-scale simulation. So calving is a big unknown in the modeling community. There is no one calving law yet that fits all glaciers. And so we hope to learn a lot from this process. So our plan is to be involved in the design of the experiments and submit our own results once the experiments are launched. Time on Asia, I'm going to go quickly here because Bill is going to talk more about this in his updates. But to give you the big picture here, this is a project that was started by Renee Weingart, who is going to talk a little bit right after us, and Adam Harrington, who provided a high mountain Asia variable resolution atmospheric grid. And you can see the whale shape in the dark black on the left-hand side that gives us a resolution of 7 kilometers to resolve the elevation in high mountain Asia. And so now that this is done, we're like, well, okay, well, let's have CESM play its role. And you can see on the top right here, it's an example of a CESM grid at 100-meter resolution of the Nepal region. And so 100-meter resolution for CESM, it's pretty high. It's going to lead to like high computational cost. And the problem with having Asia and glaciers like this, you can see there's a ice mask at the bottom on the right here, it's very sparse. So there's going to be a lot of computational waste. And while the Nepal region is very small, HMA is pretty big. So it's a highest season domain in terms of number of runs that we will have ever run. Waste project, just want to mention that we are collaborating on an NSF-funded project with many folks, and we are trying to understand what condition could have triggered the Western Antarctic ice sheet collapse during the last interglacial. I'm going to skip through this because Mia Bedar is going to talk about this at the end of this morning. And last but not least for me, I just want to remind everybody that the CESM workshop is going to take place from June 13th to 16th. It's going to be a hybrid meeting. The decision is going to be made at the end of the month. And the CSM tutorial is going to take place in August, 8 to 12. We hope to do it in person. And the registration has opened last Monday. So if you're interested yourself or have friends, students, you name it, please encourage them to register. Thanks.
Bill, you're muted.
Sorry, of course, I forgot to unmute before going into share. Let me try that once more. Okay. How's that?
Looks good, Bill.
Thanks. Okay, I'm going to talk about some modeling development plans and progress toward CESM3. I'll start by going over some science priorities, then some recent plans and progress with the model, and then some couple climate challenges that we always face and we will face this time around as well. So for CESM2, our big focus was on coupled Greenland ice sheet climate modeling. For CESM3, perhaps the greatest emphasis will be on Antarctica because that's still the largest source of sea level uncertainty and requires ice sheet ocean coupling, which is something that very few coupled models are able to do. UKESM, in addition to CESM, has this capability. In terms of Greenland, we've had some landmark publications in the last couple of years, including a paper on the transient last interglacial simulations done by Aaliyah Summers and Betty Otto-Bliesner et al. Going forward, we'd like to see if we can reduce our surface mass balance biases over Greenland and start looking at Greenland ice sheet ocean interactions. We'd also like to do more and longer runs with paleo ice sheets, including the North American ice sheet complex during the last glacial period. And for these longer simulations, we don't have the freedom so much as we do with present day and near-term future runs to fix things. So we want to have evolving ice sheet physics where we don't have to specify things like basal friction coefficients everywhere. And finally, as I'll mention, we're beginning to work on mountain glaciers, initially not coupled to other parts of the climate, but using standalone CISM with some CESM framework tools, and doing this to contribute to the Glacier MIP 3 project, which is underway. Tim van den Akker in a talk coming up will talk about some runs with the Zoot-Iverson basal sliding law, which is the latest sliding law we're using, and combines in a unified framework power law and Coulomb sliding features. And also, in the interest of simulating more realistic basal sliding, we have a basal hydrology model, which I'll say a bit about, and Sarah Bradley will be talking about later. One thing that still needs a lot of work is our calving law. We typically in runs we've done to date for Antarctica have prescribed a calving front, and we'd like to have a calving front that evolves in response to ice sheet damage in a more or less realistic way. The coupling, as Kate mentioned, between ice sheet and oceans is just about in place now, but now we need to test it and work out some of the kinks. And although we have a coupling capability between ice sheets and oceans, we don't have the ability at global scales to model some of the small scale interactions that determine how much heat gets up onto the continental shelf and underneath ice shelves. So that's something that will require parameterizations and small scale regional models, and will be a big research problem in the future. And we don't yet have a land ocean mask, which can evolve at runtime. So that's one more technical challenge still to be met before we can say we're fully interactive between ice sheets and oceans. In the interest of time, I'll skip over this slide, but this is just a comparison between features that were present in CESM 2.1 and CESM 2 the last go round, and features that are present or we hope will be present in CESM 3 and CESM 3. Planning for a CESM 3 release, hopefully sometime in the next year or so, and a draft working version of CESM 3 to be available sometime around summer of 2023. So we have a new subglacial hydrology scheme in CESM. The plot on the right shows an application of that scheme to Antarctica, where what I've shown is the basal water flux underneath the Antarctic ice sheet after the ice sheet is spun up. And you can see tendrils of water where you have much higher water in some regions, often following the topography than in other regions. So there are more complicated basal hydrology schemes out there. This is a fairly simple one, but it does have the feature that instead of just producing water locally and draining in a kind of an artificial way, it actually routes the water downhill down the hydropotential gradient and conserves water as it goes. And then the way this feeds into the dynamics is you can tie the basal water flux at a given location to the effective pressure. And the effective pressure in turn appears in the sliding law, and that determines in part whether the bed is stiff or slippery in that location. And Sarah Bradley in an upcoming talk will talk about an application of this scheme to the North American ice sheet at the last glacial maximum. And then something I'm excited about, since we're the land ice working group and have mostly been focused on ice sheets until now, but now we're starting to turn our attention also to glaciers, largely thanks to a project initiated by Summer Manala, who will be talking in a few minutes. So you may be familiar with the Randolph Glacier Inventory. It's an inventory of about 200,000 of the Earth's glaciers, divided into 19 regions. And we'd like to model these regions with these glaciers dynamically with CESM, which is something that's rarely done, certainly not at this scale. Most glacier models are flowline models or something dynamically more simple. So we need resolution of about 100 meters to model a lot of these glaciers. So is that totally crazy? Maybe a little bit, but not totally, because most of these glaciers are much more slow moving than the fastest part of ice streams in Antarctica and Greenland. Surging glaciers excluded. We're not trying to handle surging glaciers here. CESM has a time step that scales linearly with increasing resolution, which is as good as it gets. And also, there's been a huge improvement in the validation data available for glaciers. And we now have consensus ice thickness estimates for all glaciers, which were published a couple of years ago. So for starters, we have a grid for high mountain Asia, which contains about half of the Earth's glaciers in a fairly compact region. And the idea of the modeling flow is we initialize CESM with glacier outlines from RGI and with these consensus ice thickness estimates. Then we spin up the model where we compute the surface mass balance based on snowfall and surface air temperature from Reanalysis with a positive, it's sort of a simple positive degree day scheme with assuming a temperature lapse rate. And then during the spin up, we have two factors to tune for each glacier. One that we use to match the observed glacier extent and another to match the observed volume. And then after we've spun things up, then we can apply an anomaly from future climate scenarios. And this is something we hope to contribute to Glacier MIP 3, which would be a very, very different from most contributions that the glacier groups are making. And I will just finish by showing some very recent plots from a simulation of the Everest region in the Nepal Himalaya. In the upper left, here's Mount Everest right there in the middle, the yellow region. You can see the glacier outlines superposed on the surface elevation. And then after several hundred years of spin up, you can see the velocities here with a max velocity of about 200 meters per year. And then you can see the initial ice thickness and the final ice thickness. And although there are some biases here that we'll work on improving, you can see that the basic structure of glacier thickness and flow is preserved over a period of a few centuries, which suggests that this will work. Finally, I'll just say that to get a good ice sheet simulation, it's not enough to have a good dynamic ice sheet model. We need a good climate with surface mass balance input from the atmosphere and ocean models. And we do have these persistent biases. In CESM2, we had high snowfall in particular over Southeast Greenland and too much rain, which is partly an effect of overly smooth topography. This does get better, although not perfect, as you go to higher resolution. So we want to explore higher resolution or variable resolution CESM to improve these biases. We also have a high snowfall bias over East Antarctica, as shown in this work in prep by Devin Dunmeyer, who works with Jan Lennertz. And too much snowfall by something like 200 gigatons per year will cause problems during spin-up. That's comparable to the current mass loss in all of Antarctica. And we would definitely like to reduce that for CESM3. And this is something that happens with each model version. A plot that from work by Jan shows the annual rainfall in Greenland and how it varies depending on the model version. With each new model version, we have new model physics, and sometimes that physics has been developed without ice sheet specifically in mind. And so we need to work with the atmospheric modelers and land modelers so that our simulation of radiation and precipitation over ice sheets does not degrade and hopefully improves with each iteration. So this is a process we hope to be actively involved in as CESM3 is developed. So that's all for me. And I will pass it back to Jan, who's going to co-chair the rest of this session. Thanks.
All right. Thank you so much, Bill and Gunther and Kate, for the update and introduction to all the work that has been going on and is going on in the land ice working group. In the interest of time, let's use the chat for questions, remarks for all of our three speakers so far. We also have time for discussion at the end of our morning session at 11:30. But in the interest of time, let's move to our next speaker, who is René Weighaert, who I think is still joining us from Korea. And René will talk about variable resolution CSM in high mountain Asia. René, the floor is yours. So you can share your screen, hopefully.
Yeah, I think that will work. I think probably you see me now my screen.
Yep.
Yeah, thanks, of course. I gave already this kind of talk a few weeks ago on the atmospheric model working group meeting. Only changed a few slides though. So yeah, I would like to start. Yeah, okay, So yeah, this work started about 2 years ago, meanwhile. And yeah, the idea of it was to find out whether VRCSM is able to simulate the glacier surface mass balance over high mountain Asia region. So in this slide, we created a VR grid with a resolution up to 7 kilometers over the high mountain Asia domain. This is already shown by Gunther. And yeah, the idea is that we started applying CSM2 with an active atmosphere, land surface components, and prescribed sea ice and SST. And yeah, one of the most newer features in this case is that we applied a 36 elevation class scheme up to 10,000 meter altitude, which has 200 meter elevation classes. 200 meter interval elevation classes up to 7,000 meter, and then one additional virtual one. And that is a bit different from the default 10 EC elevation class scheme. Yeah, so just some facts about the time stepping and performance of this grid is that the chem physics time step is 225 seconds and the dynamics is 18.75 seconds. Model cost is about 90,000 core hours per simulated year. That is about 5% less than a globally uniform 1/4 degree SE grid. And the model throughput is about 0.3 simulated year per actual day, using around 1600 CPU on Cheyenne. The idea of also to work with a higher resolution is also to capture the highly variable topography in a better way. Here you can see some differences relative to coshare SE grids, and also compared to the input topography, which is derived from the GMTED. And especially for high mountain Asia, you see that that the topography clearly is more accurate. It's a more accurate representation, and also for example, the upper Indus Valley is more visible in the high mountain Asia grid. We did two kind of model simulations. We started with simulation 1 as a spin-up of 1 year. The default settings are like the same as for CSM2. The only thing what we changed is that we decreased the maximum snow depth to 1 meter water equivalent. However, following this simulation, we found out that the surface mass balance was not that good. So we started another simulation with more thorough spin-up procedure. We increased the maximum snow depth in order to have more refreezing capacity. We increased the ice albedo to have lower ice melt, hopefully. And we turned off long wave downscaling. We changed the rain snow repartitioning to a range that is more suitable for the high mountain Asia region. And we did some overall tunings, as well as we used updated glacier cover data set. Since the old glacier data set did not perform very well over high mountain Asia. The outputs are all evaluated by comparing with gridded outputs from globally uniform 1 degree SE grid, and further several Reanalysis satellite derived products, as well as RCM-based outcomes. So going to the results, the atmosphere part, I have some figures, but they are not finished yet, so to say. So I will leave them for later. Let's have a look at the surface. What we've learned is that we, especially over the region number 4, that is the northeastern part of high mountain Asia, is that there are warm biases during the summertime. And these warm biases, they become generally smaller with increasing resolution. However, during winter time and spring, and also a bit during autumn time, mainly over the southwestern part, which is the mainly mountainous region of high mountain Asia, we see that the cold bias is getting larger with increasing resolution. Then looking to rainfall and snowfall, we see that there's mainly rainfall bias in the monsoon-dominated region, which is region number 2. I see something fell away. It was actually the second box, so to say. The bias is larger for the high mountain Asia grids, followed by the 1 degree grids, although the difference is not that big, so to say. So it's actually, if we look at the median, you see that the high mountain Asia grid is doing slightly better than the 1 degree grid. Snowfall is mainly overestimated, as expected in the southwestern region, the mountainous region during spring, which is most likely related to the cold bias there, but also to some extent to the changed rain snow repartitioning in high mountain Asia simulation 2. Because the repartitioning makes it more suitable for having snowfall in the region, if we look in snow depth, we also see that same kind of bias, with a larger bias for the high mountain Asia VR7-2. And that could also be related to the higher maximum snow depth though. But as is the case, I try to compare with the Reanalysis data sets or satellite derived products, but also these data sets sometimes are having biases relative to the observations that are in fact not there. So it's sometimes a bit hard to compare, but in generally, the idea is that the high mountain Asia grid is doing a better job than the coarser gridded SE grids. But yeah, then the idea, that the main thing, the main research question was, is it able to simulate a glacier surface mass balance? And we learned that mainly during the first simulation, we found a very negative bias in the S&P. Fortunately, the second simulation did a good job in improving the surface mass balance. Also, the amount of grid cells at the end of the run where a positive surface mass balance was simulated tripled. And the region which was doing the best is the southeastern part of high mountain Asia, and that can actually also be seen here in the differences between the first simulation and the second simulation. Is that mainly in the southeastern part there's a big improvement in the surface mass balance, which can most likely be attributed to maybe an increase in snowfall in the monsoon dominated regions, but also the glacier surface data set did particularly a good job in the southeastern part of high mountain Asia. But yeah, the question is still, we're not still able, like so to say, there's still a lot of work going on to close this S&P bias, and there are several factors that can contribute to this bias. And one of them is that we have a cloud cover bias as well as a warm temperature bias, particularly over the Tibetan Plateau. And the potential solution could be to nudge CAM with ERA interim and ERA 5 and to see what happens. There's also some missing physics. For example, we do not take into account the hill slope aspect and orientation. And that can especially have, for example, the northward oriented glaciers have a different interaction with radiation, so to say, than the southward oriented glaciers. So in reality, there are some S&P differences. Also, there's no precipitation downscaling, debris cover is not included, and avalanching, which is technically also an important accumulation part of the S&P is also not included. Further, what could be is that the elevation downscaling in CLM, that it is currently only applied to glacier land units, and that can become an limitation, especially particular for grid cells where the glacier fraction is quite small. Since CLM, the community land model, has a grid cell mean value that goes into CAM, the land units from the glacier fraction and the vegetated land fraction, they go into that grid cell mean. But if the vegetated land fraction is quite large and has a warmer response, so to say, that means that eventually the vegetated land fraction is going to determine the grid cell mean, and that will have a negative effect on the glacier. And that I tried that to illustrate that with this this Excel plot showing the S&P at around 5,000 meter altitude, and for different glacier fraction. And you see that with a very low glacier fraction, there's generally a more negative S&P than for the high glaciated grid cells. So that brings me to the conclusions. We see temperature, precipitation biases, but also some improvements compared to the coarser gridded SE grids. Also, the snow cover observations relative to them, the high mountain Asia grid shows a better agreement, and the snow depth is mainly overestimated over the western high mountain Asia region during spring, winter, and spring, where the second simulation shows slightly higher overestimation, most likely due to snow model modifications. But if we really want to know whether it is an overestimation, we need high resolution satellite data, but those are not available for that time. So that could be for the future, maybe an option. For example, the Sentinel data could be maybe used for that. At further, the high mountain Asia grid can simulate positive SMP, but is underestimated compared to observation-based glaciological geodetic mass balances, as well as the RCM-based outputs. But we see a better performance for the second simulation, which is a good thing. We see that underestimated SMP can most likely be attributed to a combination of cloud cover warm temperature bias over Central Asia, lacking model physics, and the elevation downscaling in CLM. And that is where I want to leave it for today.
Thank you so much, René.
Thank you.
Okay. In the interest of time, let's try to keep on schedule. We're a few minutes behind. So if you have any questions for René, please put them in the chat. And René, please, if you can, answer them in the chat, and we can come back to them in the discussion too. So Samar, if you are ready to share your screen, you're working on it. That's fantastic. So we will stay in the Himalaya region and talk about modeling the evolution of the glaciers in the region. So Samar, please, it's all yours.
Thank you so much. My name is Samar, and I'm presenting some of the work that I'm doing related to the glaciers within the high mountain Asia region. So just to give you an overview of this domain, some of these things have already been said before by Bill and René. Geographically, there are a number of different features here. We have the Tibetan Plateau and a number of mountain ranges. I have named a few of them here. This region has the highest glacier density outside the polar regions, and there are over 95,000 individual glaciers. But as already has been said, these are rather sparsely spread out, especially in the Tibetan Plateau. So when we use a gridded model like CESM, it runs into some challenges, because if you're doing a 100-meter domain with a lot of empty spaces and doing dynamical runs, there are certain challenges associated with that. But for today, I want to focus on these three mountain ranges, the Himalaya, Karakoram, and Hindu Kush. So the one region here in yellow, this is Karakoram, and this has the highest density of glaciers and also the largest glaciers. So right now, one of my projects is for the Karakoram region. But I also want to point out that even though these are connected mountain ranges, they're very different geologically, but also in terms of the climate. And just to give an example here, I'm showing the precipitation seasonal cycle for two of these regions, the Eastern Himalaya in green and the Hindu Kush region in orange. So this is the long-term mean precipitation. 2 points here. First, that towards this eastern end, the magnitudes of total precipitation is quite high. So this is, I don't know if you can see, this is 500 millimeters per month, whereas on the western edge, it's almost 5 times smaller. But also the seasonal cycle is very different. For example, this region is dominated by the monsoons in the summer months, whereas this one has higher precipitation in the winter months through these winter westerly systems. And this affects how the glacier behaves. So it's sometimes very tricky if we try to use standardized parameters to run a model, because the glaciers are going to be showing very different behaviors. I also want to quickly show that there are very different geometries. So this is a very small stretch within the Karakoram region. We have the longest glacier here, which is Yachin, and this is the main stem here is around 76 kilometers. And then within the same stretch, I'm showing a couple of other smaller glaciers and then a few very small glaciers, which are only a few 100 meters long. So again, we are using a 100-meter grid for CESM, which Bill mentioned earlier, but and we have to go to very fine resolutions when we use a predict model. Okay, so the study objectives is that we want to look at the dominant physical processes which drive glacial change. And then we want to look into how the glacial geometry has changed in the past few decades and how these glaciers are going to evolve in the coming decades. So we want to establish this physical understanding first. And the science question that I'm looking at right now is the role of ice dynamics as compared to surface mass balance and driving these changes. So this work constitutes two different projects using two very different models. One of them is, of course, CESM, as mentioned before. And the other one is this very typical glacier model known as Open Global Glacier Model, OGGM. And Bill mentioned earlier that most of these models are flow-line model, and they have much simpler dynamical component. In this case, there is a shallow ice approximation, whereas with CESM, we are including this higher order dynamics. So this is quite an addition to the glacier community once we include the mountain glaciers in CESM. I'm going to be focusing more on the OGGM side of things today. Okay, I also want to quickly talk about a couple of data sources that we are using. So as Bill mentioned earlier, the glacier outlines are coming from this RGI, the Randall Glacier Inventory. We are using a geodetic mass balance dataset, which recently came out. This is global dataset to calibrate our mass balance model. And then we are using this another dataset for glacier thickness and volume. This is a consensus estimate. So 5 different modeling groups submitted their estimates for thickness and they combined it. So this is not based on observations, but this is the best we have. And we are using it for both OGGM and CESM work. Again, for now, I'm only going to be narrowing down my focus to Karakoram glaciers, the 10 largest glaciers in Karakoram. And just to give you an idea, the largest glacier here is Siachen, as I mentioned earlier. And even among these, the smallest one is GHub, which still has a length of 40 kilometers. So these are pretty long glaciers outside of the polar areas, of course. So the first step in OGGM is to get the glacier flow lines in the catchment areas. We use DEM to get these, DEM to get these. And as you can see that many of these glaciers are very complex geometries. So there is the main flow line, and then there is the number of feeding tributaries feeding into this. So of course, we want to make sure that we get the full geometry, the complex structure of these glaciers. So this is the first step. Then for this model, I'm using RF5 land reanalysis right now. So just to point out that this is not the atmospheric one, this is the land component of the reanalysis. It is final resolution at 9 kilometers, and it includes some lapse rate correction as well. For the surface mass balance, we have a very simple temperature index model where the mass balance is controlled by the solid precipitation and the near surface air temperature. We are including a similar scheme in CESM as well. And for this, we want to calibrate for this temperature sensitivity parameter. And as I mentioned earlier, to do that, we are using that geodetic mass balance dataset. Okay, a couple of quick results related to the SMB that we are seeing right now. To explain these figures, I'm showing here a triangular trend plot. So the x-axis here is showing the starting year of the trend. The y-axis is showing the ending year of the trend. So, for example, let's pick this circle up here. It is showing a trend between 1950 to 2020. The shades show whether it is positive or negative. Well, the color shows whether it is positive or negative, and the shades show how steep the slope is. So all the big circles here are statistically significant. And generally what we see is for all the glaciers, all 10 of them, the results are quite similar. That is why I'm only showing here for one of them, Kunduz. Also, for the entire region, we are seeing a long-term temperature trend, which is significant, and that this is not surprising. But when we look at the surface mass balance, the long-term trends mostly are negative. There is this small portion for quite a few of them where we were noticing a positive surface mass balance. And there is a phenomena that you may have heard of, Karakoram anomaly. Some studies a few years ago showed that certain glaciers in the Karakoram region were growing, and this aligns with the same time period. But as I mentioned earlier, that this is just a temperature index model. So whatever is happening with the surface mass balance is controlled by what is happening in temperature and snowfall. So in our case, this increase in the mass balance is controlled or dominated by an increase in snowfall during this period. So I wouldn't call this an anomaly, but also secondly, this is not a persistent trend, because as we move further in time, we are in the long term, we are still seeing a decline in the overall surface mass balance. Okay, the second part is the ice dynamics. So as I mentioned earlier, that this model uses a simple one-dimensional flow line model with a shallow ice approximation. First, there are two parameters here, the deformation, the pre-parameter A and the sliding parameter Fs that we want to calibrate the model for to get the thickness. And there are different ways, because we have two of these, there are different ways to calibrate the model. What I'm doing is I first compute A, and then there is a temperature-based relationship for that. And once I have fixed the value of A, I calibrate my model for Fs using that 5-model consensus dataset. So we try to match the volume of our model with that consensus model, consensus volume. I'm showing here the thickness, the result of the inversion after the calibration, and this is the thickness along all the flow lines for the glacier. So this is the largest glacier, and in many portions here, the thickness is over 1 kilometer deep. And so we are seeing the results that we expect. As I mentioned, that this is not an observation-based data set, so this is the best results we could possibly have right now. Okay, earlier on, I also mentioned that we want to look at the role of ice dynamics, and there are different ways to do that. One way is that we want to look at the sensitivity of glacial volume to these dynamical parameters, and I'm doing that here at steady state. So what I did is, this is the normalized parameters, and I increase it by a factor of 10, or decrease it by a factor of 10, and then see how the volume of the glacier is going to change. So for most of the glaciers, the response is like the figure on the left. They are sensitive to A, but mostly they're more sensitive to the sliding parameter. But then there are a couple of glaciers where I noticed that changing A does not make that much of a difference. For example, Hispar is far more sensitive to the sliding parameter. And just the way I have set up my model, it simply says that this is not that sensitive to changes in temperature of the glacier, because that is how I'm computing my A. But again, I do want to point out that this is work in progress, and we are trying to refine this further to make sure we understand the results properly. Okay, the final part is the dynamical runs, and for now I'm only looking at the historical period. And there are different ways to deal with the dynamical glacial evolution as we go back in time. One way is that we fix the geometry up till the date where we had the glacier outline. So this dotted line that you're seeing here for the year 2001 is when we have the glacier outline from RGI for this Siachen Glacier. Another way is that we do a dynamical spin up where we go back in time, say starting from 1980, and we do some iterations to match, to run forward and match either the area or the volume at the RGI date. So the three things is, first, we either fix the geometry, or we do a dynamical spin up to match the area at RGI, or we do a dynamical spin up to match the volume at RGI date. As you can see here, that I'm only showing two of them, fixed geometry and dynamical spin up to match the volume, and then they're showing different results. The magnitudes are not that far off, but if we just look at even the trends, they're different. Again, here there's no right or wrong way to do things. And the way we set up our model is going to produce some different results. I don't want to spend too much time here also, because this is work in progress, and we're trying to make sure that our model setup is right, but also we're trying to interpret these results correctly. So I want to summarize with a couple of points, very generic points. Whatever data sets that we use for this region, the larger high mountain area region, it is going to have some limitations and biases, because there are not that many field-based observations. So there are only a few, I think 4 or 5 glaciers where there are field studies. And we have to rely on these global data sets. If we can, of course, tune our different parameters to match these baseline data sets, but we also want to make sure that whatever we are doing produces physically consistent results. And what I mean here is that, for example, there are different ways to tune for the sliding and the deformation parameter. The one I'm using includes both of them. There is another way where generally people make the sliding parameter 0 and they only tune for A. And I don't think that is particularly feasible for these glaciers. Finally, of course, there are different model setups, and then there are different methods to do those runs, like I showed in the dynamical runs in the previous slide. And they would produce different outputs as well. So we should be careful when we're trying to interpret the results. Otherwise, we can just produce any result that we want to sell to the audience. And with that, if you have any questions, I'm happy to answer those.
Thank you so much, Samar. And thanks for sticking to the time too. Much appreciated. So again, I think using the chat here could work well for asking and answering questions, and we can keep some items to the discussion or bring them back. Let's move to our next speaker, who is Ute Hertzfeld. And Ute will, I'm sure, remind us how complex the cryosphere is using observations. So Ute, please go ahead.
Hey, Jan, thanks very much. So I assume you see the screen, right?
Yeah, we see the screen, but it's not your presentation.
Yeah, it's fine. It's not
PDF
supposed to be full.
Yep.
There's a reason for this. Okay, I want to see, anyways, I want to see you and I want to see the time.
Okay.
And there's some surprise videos for you.
Okay.
Okay, so thanks for giving me a time slot to talk here. I'm actually really excited about the move of the modeling community towards high resolution model implementation. And I just want to say this right at the beginning. The fact that we have observation at decades of like 50 meters right now does not mean we are getting all the processes. So we are moving towards picking up new complex cryospheric processes in analysis of decimeters, like sub-meter scale to 5 meter scale. And so that's what this talk is about, with a heavy bias on modeling surge glaciers. Talks co-authored by Tom Trano, who's the modeler in our group, Adam Hayes, who works on atmosphere and ice, Hui Lin, who's a new student, Jack Hesberg, and also by Ellen Buckley and Sinead Farrell, who are our collaborators at the University of Maryland for the CS component. Okay, so here are some of the components. We see the changing cryosphere in the left. You actually see my mouse. Do you see my mouse? You should. Okay, so you see the changing cryosphere, fieldwork we collect, and the right symbol stands for algorithms for high resolution data analysis, ISA2 in this case. So we'll cover some of the related topics, including the validation campaign, fractures and drifts in Pine Island ice shelf, and melt ponds and ridges on the Arctic ice sheet. This is mostly the slide of Nick Ribri, and everyone in this community is more than aware that ice dynamic processes contribute to sea level rise. But that's from a talk I gave to computer science. Okay, specifically, we see the surge glaciers, which Bill said is the part of the part that CESM can't handle as of quite yet, because everything else it does pretty good. We can have really fast moving glaciers like Nikibrien and Svalbard here moving at 22 meters per day, creating a really rough crevassed surface right next to Ordnanzbrien, which is moving slowly, and you see plenty of ice-ocean interaction, which contributes about 1% of global annual sea level rise from a single glacier in a few months. So that's just to say it matters. Another thing such a surge glacier is good for is validation of satellite data products, because after all, we have really complex and very different, morphologically different types of ice surfaces in close proximity. So these days, pretty much, not most, but well, most but not all of my time is absorbed by making algorithms for NASA's ISA2, but I really love working on and trying to model these glaciers. Okay, so here you can see this is from another campaign, 2019. You can see ice-ocean interaction up to changes of dirt on the glacier, which is the model, which is the moraine, which shows you the difference between, well, it's sort of velocity gradient. And the complex one, as you see, like the boundary is really not straight. So here you have fast moving ice and the folded moraine shifts as the velocity dominance changes where it occurs. Okay, here are velocity maps made from Sentinel, which shows you, just note the scales different, highest velocities in 2017, and such a surge glacier in Svalbard surges for something like a decade, so it still is surging, while due to COVID, we couldn't go there the last 2 years. We're hoping to go this year, but who knows? So now, to the problem of why we want to, okay, go.
0.2 microradians. That's the angle of pointing stability of the Atlas laser. If you placed a silver dollar 28 miles away from Atlas, the laser's center would stay on the coin. That kind of stability is absolutely critical for the spacecraft to measure the height of Earth from orbit. Atlas uses the beam steering mechanism, which is a motorized mirror that moves to compensate for thermal changes that happen in orbit and prevents the Atlas beams from bending as they head for Earth.
Okay, so this is the type of accuracy we're dealing with. And now to the type of data analysis you have to do.
532 nanometers. That's the wavelength of a bright green color, the color of the Atlas lasers measuring the elevation of the Earth below. When Atlas receives the photons back from Earth, it has to filter out the sunlight that naturally reflects off the Earth, which would overwhelm the detectors. So Atlas only lets in light that is exactly 532 nanometers. Sunlight in that wavelength range will also set off Atlas detectors. And so computer programs are needed to filter out those sunlight photons in the data.
All right, enough said about this. So this tells us we do need different mathematics, and it's a it's a difficult problem from a noise. Is this now moving here? Now, okay, and so then it results in this really complicated foot beam pattern on the ground. I want to use these outreach videos, okay, to show why we need a different algorithm to actually detect the complexity of the Earth in ISA2 data. And we are working on this new algorithm called the density dimension algorithm. It's not that new, I've had it for a while. The goal is, and it allows us to show the existence of crevasses as opposed to just interpolating right over them as the standard product does right now. Okay, so you can see, so top and bottom is the strong beam and the weak beam. We can find crevasses with the DDA ice algorithm in strong beam and weak beam data, which means for something like an Arctic glacier, we have lots of tracks crossing that glacier, but there are still gaps. The algorithm also finds smooth surfaces, as you can see at the bottom right panel, and it has a capability to switch back and forth between interpolating for crevasses and just interpolating for a smooth surface on the Greenland inlet ice. So you should just look at the bottom. The rest is how we get to where we want to be. The characteristics of the DDA ice are, it starts right from the photon point cloud, as this video in Mickey Mouse venue tried to relay to the audience. And it reserves at the point cloud resolution of the data, which is 70 centimeter, whereas the official data product reserves at 40 meter postings every 20 meters. So we cannot find crevasses or fractures in the currently posted product, but we are hoping to be able to implement this. We are actually working on implementing this for the entire Greenland ice sheet, and it will be shared sometime soon. Now, in order to validate whether what we see is actually fake or whether crevasses are crevasses, and they are where we think, I fly the validation campaign. We were able to fly 2 of them in Greenland and Svalbard over a surge type glacier. The left panel actually gives you an idea how dense the tracts actually are. We're setting up GPS stations and so forth. And all thanks to the Norwegian Polar Institute, which let us charter their helicopter without additional overhead or anything. Then we do some fancy GPS and correct all the data, and we just had a 40-page paper coming out on how we do this. And I guess that's not of so much interest for this community. This shows the comparison between airborne altimetry and actually ISA2 altimetry from several months later, and in short, it matches. Okay, so the more of the details are shown in this paper. That's a page from the analysis of geodetic data. So in short, for modelers, crevasses are where they are, and we match within like decimeters of the depth of a crevasse, which is sort of unheard of to this date. But so that will allow the modeling community to move forward with things like fractures. So how do we put fractures in the easy? So the hard way is you model the fracture directly. The easy way is you create a parameterized product, which is surface roughness, which shows you where crevasse fields are. And that kind of a thing is approximately sufficient for a lot of the modeling studies, because you can do this at a lower resolution and then provide this type of information to whoever wants to model this, or we use it ourselves. Tom Trano has actually used it in his PhD thesis, which is long completed. So this gives you an overview of like the ENF, the photographs below align with the type of terrain we see. And you can see crevasses, whether they're full of water or not, in both the high resolution data and the low resolution data. And you can, like, each plot is a kilometer. I mean, it has the scale, but I realize I might be going too fast for people to read everything. Okay, now with a 2. Now we have taken a look, Tom Trano specifically took a look at all the RGTs, which are the reference ground tracks ever collected over Necribrien from January 2019 to December 2020. And you can see now that we are able to follow, say, the drop of the glacier, right? So you can see at the edges, ice sheet height does not change, whereas in the middle, it does change. So that means it's not a climatic signal. It's a signal that actually shows you we have a surge collapse, right? So we can actually go from observations to processes. It also shows you where crevasse fields formed, but it doesn't make, like other algorithms would, leave out this crevasse field, not be able to calculate height change. We are able to calculate height change despite of crevasses, even if you're not into crevasses. However, if you are, or if you want to use fracture in your model, then you can see where fracture occurs and to what amount. And so this is sort of the repeats, right? You remember this little kindergarten video? You see the tracks repeat, and the ice surface then gets monitored every 91 days, weather permitting. The weather is always shitty where all these surge glaciers are. So then we can calculate surface height rate of change, for instance, for the entire glacier, or roughness rate of change. So now here are our group's modeling approaches. Tom uses Elmer Ice, which is a 3D full Stokes environment. And in his thesis, he creates a search model of the Bering-Berkeley glacier system, which is a temperate glacier. And now we're moving towards including the Necribrien glacier system in Svalbard. This requires at the minimum surface topography. So the cryosat was for Bering Glacier, because of course you have to have topography from when the glacier surged. Bering surged before ISA2 launch. Necribrien surges now with ISA2. And as everyone in the modeling community knows, the basal sliding law is the most important boundary condition. So now, what's the problem with modeling Necribrien? We would like to have a 3D full Stokes search model. We've made some feeble efforts to get there. To constrain basal sliding, we need base topography, but the current base topography is only based on 2 or 3 tracks flown by the British Antarctic Survey in a long time ago and turned into this bad topography model. So it's correct and it's off. That's a big problem. The next thing is, of course, Negri Brean is an Arctic glacier, so it is a polythermal glacier with a different type of thermodynamics at the top and at the bottom. So implementing that requires more work than just running Bering Glacier environment over Negri Brean. That's not going to get us where we want to be. The current results are more there for demonstration of purpose, like Tom would not be presenting them because he thinks we are not where we want to be. But it just sort of shows we have some demonstration of concept that we can run over Negri Brean despite of all these constraints.
1 minute, Ute.
1 minute, okay. So here is a new start for a different glacier. This shows out of the ISA2 data, we can actually also get calving and drifting in Pine Island ice shelf. And since this is for the polar community, we have a really exciting development collaborative with Sinead and Ellen Buckley at the University of Maryland. We can get all the melt ponds in a large area of the Lincoln Sea by having something that we call the DDA sea ice bifurcate. It automatically decides as it runs along the track whether there is a pond or not, which means it bifurcates. So you can detect melt ponds, even melt ponds in rich environments. And so the exciting thing for me is that we will move, like the ISA2 project actually will move towards implementing this high resolution sea ice product in the near future, which is we have been given the go-ahead to look into how to change the current really low resolution data product, which totally misses melt ponds and whatever, because it's not designed to do that, and implement that as in the future. So there will be all this information available for the CS community. These are the modeling steps which you don't need. And then the remaining 3 or 4 slides are just the references. Okay. All right. Thanks for the extra minute.
Thank you, Ute. Thanks for sticking to the time. Appreciate it. Again, if you have questions for Ute, please add them to the chat. And that gives us time to move to the last speaker before we take a 10 to 15 minute break. The last speaker of our first session is Tessa Gorte, who will be talking about the impact of Antarctic mass loss on the Southern Ocean.
Yeah, thanks, Jan, and thanks, Ute, and to everyone else who's been giving great talks this morning. So I'll try and follow up with another decent talk. I assume you all can see the screen all right?
Yes, go
Fantastic.
ahead.
So as Jan was saying, my name is Tessa Gorte, and I work with Jon and Nikki Lewandowski at our department at CU, Atmospheric and Oceanic Sciences. And we work on, I'm forcing them to work on modeling satellite-based Antarctic melt as it leads to higher Southern Ocean sea ice extent by 2100. And I'd like to thank my funding sources, NASA and CU Boulder, as well as NCAR for the computing resources that have been absolutely vital to doing this work. So as you likely already know, the Antarctic ice sheet is losing mass. So this is a video that shows data from the Gravity Recovery and Climate Experiment satellite, so GRACE. And you can see that over time, the ice sheet is losing mass. And so these redder parts indicate mass loss. And so as you likely already know, a lot of this mass loss is focused in this one region that we refer to as the West Antarctic ice sheet, or WAIS. So, we know that that's losing mass from our satellite data. Unfortunately, this mass loss throughout WAIS is not typically well represented in climate models. And so we, it brings us to our fundamental sort of guiding research question is what happens if we try to mimic a more realistic freshwater forcing by using these satellite data and incorporating them into a climate model. So we were leaning on CESM2 just because it's a great model and it's nice and close, and we have all this free open access data. And so we created 2 simulations. The first is a control simulation with constant freshwater forcing from 1970 to 2100, and it's based on De Poorter et al. 2013. And then we have a second simulation, which we refer to as an IMBY simulation, which increases linearly from 1992 to 2020, which is based on IMBY team results here on the right. And then from 2020 to the end of the century, we base our forcing on DeCanto et al., which from 2020 to 2050 is roughly constant and then increases at roughly an exponential rate from 2050 through the end of the century. So if we take those two figures on the right, the top one is showing mass change and the bottom one is showing contribution to global mean sea level. So if we reorient that top one so that they're both kind of showing mass loss, we can then sort of take them together and create a piecewise function that kind of mimics our freshwater forcing, where again, from 1992 to 2020, it increases linearly, and then from 2050 to the end of the century, it increases roughly exponentially. And so we can also plot our GRACE data on top so you know what those look like, and then our control simulation, again, constant in time from 1970 to 2100. And so if we take that time series on the left and we reconcile it with our map of mass loss that I showed before, all of the additional fresh water from the INBI to control simulation, so basically the difference between these two lines here in this time series, was all put into this, like what we call our waste basin, which is roughly the sort of Amundsen Sea and Bellingshausen Sea mask in CESM. Our freshwater forcing was also split between basal melt and calving forcing, and we ran our simulations again out to 2100 using the fully coupled framework, though an inactive ice sheet component under SSP 585. And our major focus was part of the sort of POP response to how does this freshwater forcing impact the ocean. So with that, one of the first things that we wanted to look at was sea ice. And so for someone who's not a sea ice modeler or really a sea ice specialist in general, my very basic understanding going into this was that if I have fresher water, that should make sea ice easier to form. And so we do in fact find that by the end of the century, there is more sea ice in the INBI simulation across the Southern Ocean than in the control, to the point where it's essentially comparable to CESM2, the large ensemble, which I've plotted here in gray. So you have INBI in light blue, control in dark blue, and lens in gray. And lens is run under a slightly different forcing, SSP 370. And so the way I like to think about this, at least in a qualitative sense, is that changing the freshwater forcing in CESM is tantamount to sort of changing an atmospheric forcing. So a really significant impact for Southern Ocean sea ice in particular. And so I'm going to talk about how this is realized in a spatial sense, but before I do, I need to sort of run through, I'm going to go through quite a few postage stamp plots, and I want to make sure that I run through that so that you all know what I'm talking about. And so I'll show a bunch of basically 3x3 plots where I'll show output from the INBI simulation in the top row, control simulation in the middle row, and then the difference in the bottom, with the beginning of the century on the left-hand side, the end of the century in the center, and then again, the difference here on the right. And so if you want to compare between simulations, you should compare vertically. And if you want to compare over time scales, you should compare horizontally. And so what that looks like with real data is something like this, where you have your sort of time comparisons going across and your simulation comparisons going down. And so this figure is ice fraction, so present here. And you can see that the INBI simulation shows absolute sea ice growth off this sort of Amundsen and Ross Sea coasts that is not replicated in the control simulation, and that growth is really well co-located with our freshwater input. And then generally speaking, there's also less sea ice loss throughout most of the rest of the Southern Ocean as well. And so to get at the sort of drivers behind this, we first looked at sea ice growth. And so I have my sea ice growth terms here: frazzle ice, congelation ice, and snow ice. And this main subplot shows the entire Southern Ocean, and then with a breakdown of different basins on the top there. And you can see that through most of the Southern Ocean, there's not much difference between the simulations for congelation or snow ice formation, but there's obviously quite a large difference in frazzle ice formation. And that is mostly attributable to changes in the Bellingshausen and Amundsen seas, as well as a little bit in the Ross Sea as well. And so if we focus on the Ross and Amundsen seas a little bit, we wanted to look at the freshwater just to make sure that, in fact, our salinity was doing what we were hoping. And indeed it does, where in the largest change of salinity between the two simulations is, again, right off these like Ross and Amundsen seas, where unsurprisingly, where we've put in a whole bunch of fresh water, it is indeed quite a bit fresher. There is also some freshening off the East Antarctic coastline as well. And it kind of makes its way all the way up to like the Amory ice shelf roughly. Because SST and sea surface salinity are inherently linked, one of the next things that we looked at was sea surface temperature. And so we did find that, both simulations warm throughout the Southern Ocean, unsurprisingly, given the atmospheric warming scenario, but there is quite a bit of difference in change in SST between these simulations. And so the IMBY simulation increases by roughly 1 degree C versus the control that increases by roughly 1.5 degrees C over this course of the 21st century. And if we look at, again, what that looks like spatially, you can see that this relative cooling signal, again, it is warming the IMBY simulation, but it's cool relative to the control. That signal basically permeates through most of the Southern Ocean with some small anomalies, particularly in the Weddell Sea. I will say a little bit of a caveat here is that there's not much of a difference in global SST, so there is a sort of interesting response going on in the Northern Hemisphere as well. So I will say, despite cooler sea surface temperatures, there is significant subsurface warming. And so this plot shows temperature at 100 meters depth. And there's significant subsurface warming between the Bellingshausen Sea and the Amory Ice Shelf. So over here, all the way to the Amory Ice Shelf, and you can kind of see this like large warming signal at this depth. And that signal permeates all the way down below 500 meters depth. So a really strong subsurface warming signal that we see in this simulation. So if we go back to our sort of major research question here, and we sort of ask what happens if we rewrite this model forcing, we find that there's a fresher Southern Ocean surface, which is not surprising. And that leads to less loss of Southern Ocean sea ice. And we also see cooler sea surface temperatures, but more subsurface warming. So those three things are all sort of playing into each other and you know, affecting one another. And so I want to know basically, how does changing these three things affect other Southern Ocean thermodynamics? And so specifically, what I'll talk about in this talk are how it affects mixed layer depth, sea surface height, as well as the meridional overturning circulation, or MOC, what I refer to as Mach, what I think most people probably don't refer to as Mach, but that's how I say it. So apologies for that. But we find that there's a sorry, that's not supposed to say deeper. That's supposed to say shallower. There's a shallower mixed layer depth in the IMBY control, or in the IMBY simulation. Oh yeah, so great. So there's a deeper, sorry for this. This should say shallower up here, but deeper in the control simulation than the IMBY simulation. So you've got mixed layer depth here. And you can see that for the IMBY simulation, particularly in the latter half of the century, you've got something that is, you know, roughly 70, 71 meters deep, versus the control that is not really changing over time, hovering around 76 meters. And then if we look at sea surface height, both simulations show a pretty strong sea surface height drop, but the IMBY simulation shows quite a bit less. And if you look at the 2070 to 2100 range, there's a difference in almost like 1.5 millimeters per decade over that period. So a pretty significant change in how the sea surface height responds to this. And then finally, so I'm going to be talking about the MOC stream function. I was not so familiar with stream functions, so I'm just going to go through how this looks really quickly. So you've got latitude here on the x-axis with depth on the y-axis. And so positive means that there's sort of clockwise vertical mixing, which gives you a sort of curl that points west. Negative gets you the opposite. And so this big red blob that you see there is like the AMOC signal, for instance. And so if we go back to our fun postage stamp plots, the things that some of the big standout features by the end of the century are that the Deacon cell moves further northward in the IMBY simulation, and that there is a weakening of the AMOC slowdown signal, which is, you know, this very like well-modeled phenomenon. So this is a really interesting response that we find from this Southern Ocean freshening signal. So just to conclude really quickly here, in the IMBY simulation, we see freshening and a relative surface cooling signal. We also see that results in less of a loss of sea ice by 2100. And then that finally results in a shallower mixed layer depth, less sea surface height drop, and relatively stronger AMOC. So yeah, so that's my presentation. Again, happy to take any questions in the chat for the sake of time. And yeah, I'll be around for the discussion if anyone has any questions for that. So thank you.
Thanks so much, Tessa. And right on time, or even, you know, we're at 10 o'clock sharp, so that's awesome. Yeah, let's thank all our speakers of our first session. And if you have any questions for any of them, please use the chat, and we will take a well-deserved break for, let me check, 30 minutes, which is fantastic. So plenty of time to, you know, take a break, drink something, eat something, have dinner for those of you who are in Europe. And we'll see each other in 30 minutes. So 10:30 Mountain Time to start our second session. If anyone wants to, keep on discussing, of course, this Zoom link will continue to exist. And if you want to stay on and talk, that's also possible, of course. Thank you. See you in 30 minutes.
Gunter, will you be introducing the speakers for this part?
Yep.
All right, thanks.
We have 1 minute to go before the break ends. And for everybody, there's great discussion happening in the chat. The chat will be saved, so so there's no loss of ideas here. You can always refer to it. So keep it going. All right, it is 10:30. Welcome back, everybody. I hope you had a great break. And we're going to get our second part of working group going. Our next speaker is Sarah Bradley, and she's going to tell us a little bit about improving the incorporation of ice stream in North American ice sheets. So Sarah, the floor is yours.
Okay. Hello, hopefully I'm unmuted now. Yep. Hiya. So I'm going to give a talk today on some work myself, Bill, and colleagues at Sheffield have been doing on modeling ice streams of the North American ice sheet complex at the last glacial period. And we've been really focusing on what's the role of glacial hydrology and subglacial geology. So, oops, this is going to work. Oops. So people often look at the last glacial period. There's an ice sheet across the North American complex when you have the Inuitian ice sheet, the Laurentide ice sheet, and the Cordillenian ice sheet. And you've got some good estimates of the total sea level volume at this glacial period of 76 and a bit. And there was this lovely study by April Dalton in 2020, where we have a really good handle on the spatial margins through time. But we want to look at a different approach and look into the ice streams. So there's an empirical evidence record across North America and the Cordillenian, but it was in a different paper, looking at the major ice streams that were active during the glacial period. And this comes from landform evidence, moraines, eskers, lineations. And you get lovely records such as this map here, taken from Martin Margold's paper, where these sort of dark blue triangle areas are where you think there's active ice streams during the glacial period, such as these lobes to the south, the Hudson Strait, and the ones through and into the north. And there's a few suggestions of a hierarchy of what controls these ice streams formations: topography, calving, sediments, or flowing over somewhere that's quite soft, meltwater, or global geothermal heat flux. So we want to look into what are the suggested mechanisms for this record of ice streams. So the ones that I've crudely highlighted in red, these flow into the marine terminating areas, and it has been suggested that these are topographically controlled. So they form because they're steered down an ice trough. And this is a map of our paleotopography at 21,000 years ago, where obviously blue is what would be below sea level and green is land, with the empirical record of ice streams drawn on the top. And as you can see, the ice streams do lie in some nice troughs. So it would be logical that you would assume they form due to topography. Then you have the ice streams to the south, and I don't live in America, but I'm informed that it's quite a low relief. So this margin is very flat. It's underlain by soft sediments, and obviously the margin is land terminating. So it was suggested that these ice streams form due to the soft sediments the ice is flowing on. So you have this contrasting regime between you have the southern margin where the ice streams form due to the bed, and then you have the northern and northeastern where they form due to topographic steering. So this is what we wanted to look into. So we had kind of two big questions. Can we, with the CESM model, make this inferred pattern of ice streaming, which hasn't necessarily been done before? And if we replicate it quite well, can we look into why the ice streams form? Is it topography? Is it the sediments? Or is it something to do with meltwater? So obviously, we're in an NCAR talk. We use the CESM 2.1 higher order model, but we run most of our simulations at 16 kilometers just for speed, as in human time. But then our final runs, we're going to run at 4 kilometers to kind of get a better influence. This is our starting ice sheet reconstruction for the North American ice sheet. It's taken from GLAC 1D from Les Karasov. we don't have any preference. We just use that as a starting one. We tried the runs with 2 sliding laws. I know Tim's going to talk more about the Zout-Iverson law later, but we've also repeated the runs with the more traditional pseudoplastic law. Bill has nicely updated an old scheme for hydrology routing inside the CESM model, where it routes meltwater based on the hydraulic gradient. So we can use this scheme to see what is the influence of water flowing below the ice sheet on the ice stream formation. It's not an amazing hydrology model, they're not completely coupled, but it's better than what was there previously, where there was no sort of spatial variation in the hydrology model. And obviously you need some form of glacial forcing to run an ice sheet model, and we use a surface mass balance and a surface temperature from some CESM 2.1 glacial runs that we've completed. This is an example of the surface mass balance, and one thing to note is it has a very large ablation area along the southern margin. So our reconstructions will never perfectly match the margin due to this large negative balance, but these are our forcings. So we wanted to look into the influence of the surface, the subglacial bed. So a typical way you do this is you use something called a till friction angle map to represent where the ice sheet might be sitting on bed with a different strength. And it's kind of sort of an arbitrary sort of name for given to something, of supposed to define how a material will fracture when its yield strength is exceeded. So it's sort of a map of bed strength, where if you have a very small till friction angle, you assume it's got beds, the material is very clay rich and weak, and vice versa, it's got a really high till friction angle, it's very strong and won't flow as weak. So we have this map here where you've got 3 different transitions of till friction angle. So Evan Gowan in 2016 published this paper of data sets for North America on different observations of sedimentary rock, different data sets to make till maps. So we combined Evan's publication of grain size data sets, where you have areas of silt, which is mostly the green, which is most of North America, and then areas of sand, and then overprinted on what was the ice streams from the geomorphological record, which are weaker. Now, it's quite coarse, you've only got 3 different values, but we've tried it with 2 or 3 different values, 1 value, changing the numbers around a little bit, and the broad patterns are kind of the same, and you're adding in more detail that you're probably going to get that you actually know about. So this is our, what I will call is input information on geology. So the key question is, can we replicate the pattern of streaming? So if we look at the figure on the left, this is surface velocity at the end of our equilibrated runs. The light blue line is the starting ice sheet extent. And so to give you an idea of how much the ice sheet is retreated due to this large ablation area, so we don't capture these southern lobes. The dark black dashed lines are where the landform evidence suggests that there is ice streams, and the pale green line is where I've just tried to contour what is defined as areas of fast flow. So it's sort of a summary plot before we get to more of the interesting details. What we found was that the ice streams that form along the Cordillenian ice sheet were mostly controlled by the inclusion of topography. The ones along the southern margin, such as the publications have suggested, are strongly controlled by the inclusion of the bed strength of geology maps. What was more interesting is if you include Bill's new hydrology scheme, it mostly impacts the ice streams flowing here to the north. It didn't have any impact on the Hudson Strait ice stream, which was surprising because it's often thought to form due to the trough and flux. This is some other output they were producing by Anna Ignacia, which is some flow line routing, which you were using to sort of look at the change in the drainage basin. So you can now go to sleep because this is a summary map of what forms the ice streams across North America and how well we do it. But then to get into some more modeling detail. So we tried the 2 sliding laws, and these are just movies of the last 10,000 years. The main thing to take home is if you use the older scheme, the pseudoplastic law, the ice sheet is about nearly 10 meters sea level equivalent volume too large. So the ice sheet is a Greenland too big. So it just really, really thickened, mostly because the ice streams are a lot slower. So that's the first difference. The ice streams are often not as elongated. If you look at this one, I think it's called the Lancaster Sound. There's slightly shorter. So there's some differences between the two sliding laws, but the newer law performs better in the spatial extent of the ice streams and in the total volume. So that was quite nice. So now we look into the different controls on the ice streams, basically what I showed in the summary plot. So if we run what would be classed as, do we form spontaneous ice streams? If we run the model on a flat bed with no input bed strength, then you don't really get any ice streams, which is to be perhaps be expected. You don't form spontaneous ones. So this now the plot. So you're comparing left-hand plot to the right-hand plot. So we're running on a flat bed, just with information on geology and topography and geology. And what is interesting is the Hudson Strait ice stream and the ice streams to the north, you form nice ice streams, even though there's no troughs. And these ice streams were thought to form due to the topographic steering, and yet this isn't the case from our results. Now, whether it's because there's an imprint in the initial surface topography that's influencing how the ice sheet flows, we were not very sure as of yet, but it was interesting that removing the topography, you don't get these ice streams. Then if you run with just topography and no changes in bed strength, so they have a uniform bed strength across the ice sheet, you lose the southern ice stream, so they're strongly influenced by the topography, and you lose this nice ice stream in the Hudson Strait and the ones falling to the north. And we found this quite surprising because it's always suggested that these are formed due to the control of topography. So the next thing was, we've introduced this nice new hydrology routing model, and you can produce lovely maps like this. This is a map of the basal water flux below the ice sheet, and you get these huge fluxes of water below these three major ice streams over 2.5 meters per year, which is great. But we wanted to ask the question of, is this important for forming the ice streams? If you have no water at all, which ice streams turn on and off? So now this is again the same run. We run on a bed with some topography. We input the sediment information, but we do not include the water. So the effective pressure below the ice sheet is just related to changes in temperature. So there's basically no water and no water routing. And the only ice streams that seem to be really important is this ice stream here is strongly lost, when the rest of them don't seem to be so dependent on it. So this is something we want to look into further. So we've ran some last glacial period. The North American ice sheet was drained by multiple ice streams who's recorded in the landforms. We've run 16-kilometer runs forced with a new climatology, sediment map, and sediment routing model. Can we make the ice streams? Yes. Have we made a first order attempt into looking at what's controlling them? Yes. Maybe it's a bit ambitious, but we want to look into further how the hydrology and the sliding laws are really related. And a second thing which motivated this work was investigating the amount of discharge from both of all the network of ice streams. Because in 2016, there was this, when the landform maps were published, Chris Stokes compared the empirical evidence of the ice stream discharge to the discharge from an ice sheet model, which is this green line here. And the empirical evidence suggests the data is an ice stream discharge of about the order of 2 kilometers cubed per year, but the models were suggesting 5. So there's just a huge mismatch between the models and the empirical data. So our next step is to see if we're using this better model with a higher order ice physics and better hydrology, will we kind of reconcile some of this problem? That's it.
Thanks a lot, Sarah. So there's a little bit of time for questions, but for fairness with everybody, please post them in the chat, and we'll move on to the next speaker, which is going to be Heike Goetzer, who's going to talk to us about the copper Greenland ice sheet climate simulation with the Norwegian Earth System model.
Thanks,
So
Gunther.
Heike, go ahead.
Can you hear me well?
Yes.
Great. Okay, I'm trying to do the share here. All right. So I will talk about some developments that we did with the Norwegian Earth System model. And I've listed here to acknowledge my Norwegian colleagues, but I want to emphasize here that this is highly supported by work from different people in the Land Ice Working Group, and I'll come back to that later. So yeah, the whole point here is to do coupled climate ice sheet simulations with the Norwegian Earth System model, including a dynamic ice sheet model, the community ice sheet model. So NORSM itself is a CMIP type model that has been mainly developed in Norway. And in this work, we are for the first time including a dynamic Greenland ice sheet model to allow for two-way interactions between climate and ice sheet. And so NORSM itself is strongly based on CESM, as you may know. The notable differences are the ocean component, which is completely different. This is an ocean model that's been developed in Bergen. And also this iHammock, which deals with the biogeochemistry, is a new component compared to CSM. And there's also notable differences in the chemistry and mainly in the aerosols in the atmospheric component. But when it comes to the interaction with the ice sheet model, CISM, this NORSM is very similar to CSM in that we inherit all the coupling infrastructure through the land model, for instance, and also the update of the atmosphere. So the ice sheet climate interactions that we want to address here are the surface mass balance height feedback, which is basically handled by the land model through these elevation classes, freshwater fluxes influencing the ocean circulation, which, by the way, are also routed through the land model, so there's no direct connection to the ocean here. And then atmospheric circulation changes due to changes in ice sheet topography, which is done by updating the restarts of the atmospheric model. At the moment, we do not have a mechanism to account for direct influence of the ocean on the ice sheet, which should be done, but this is a problem of high resolution, basically, because we need to force these small outlet glaciers that are in contact with the ocean, and that's something that we'll be working on in a forthcoming project. So I just want to emphasize here again that all of the coupling that is happening here between the ice sheet and the rest of NORSM is kind of very strongly based on development that's been done at the Land Ice Working Group. So to run these coupled simulations, initializing the ice sheet and initializing the coupled ice sheet climate system is important. And this is a challenging task, mainly because of the biases in the climate forcing. So the ice sheet model has to be relaxed to the climate model surface mass balance. And then the climate model, so NORSM, has to be relaxed to ice sheet geometry, albedo, and freshwater fluxes. And in all of that, biases in the surface mass balance typically lead to biases in the geometry and or in ice sheet dynamics. So I'm illustrating that here with comparing high resolution surface mass balance product produced by a regional climate model, RACMO, this is for the historical period, 1960-1990, and comparing that to what comes out of NORSM, high resolution NORSM at 1 degree atmosphere resolution and a low resolution NORSM at 2 degree atmospheric resolution, which don't, on first view, don't look so different, but you can see that this precipitation is smoothed much further inland here in the low resolution version. I'm showing only results today of this high resolution NORSM. But you can see that overall, we are missing some of the ablation zones here in blue around the margin. And yeah, as I said, the precipitation smoothed much further inland. So this is something that we're trying to work with in the initialization that I'm getting to next. So the process that we chose for initialization here is kind of motivated by work that we did for standalone ice sheet simulations. So the idea is basically that all of the uncertainty that comes from the surface mass balance is kind of pushed away into tuning the basal friction coefficients and matching the observed geometry Nevertheless, what we also do here is that we mask all the ice outside of the observed ice sheet extent and add that as freshwater flux to the ocean. And yeah, I have to just say that this is a very strong constraint on ice sheet evolution. And I think is only justified in these particular experiments here, because as you will see later, I'm forcing the ice sheet with very strong emission scenarios where I expect the ice sheet to retreat. But in any other situation, this is something that probably shouldn't be done. And finally, we relax the NORSM SMP to a slightly biased surface mass balance from NORSM2, which makes that the historical trend is that the ice sheet is tentatively losing mass rather than gaining it. And this was introduced after initial tests where we saw that even if the ice sheet was relaxed to the NORSM SMB, we saw a mass gain over the historical period, which we didn't want, which is not in line with observations or reconstructions. So this initial ice sheet we assigned to the year 1800, and that's the moment when the coupling happens. And then from then on, we run coupled simulations forward in time. So I'm showing here results that go all the way to 2300. And here are the experiments first that I'm doing. So initially, I have this spin-up period of 50 years. The reason why I only need 50 years for this coupled spin-up is because I have so highly constrained the ice sheet extent and geometry. So the ice sheet that goes into these simulations looks very similar to what the standard NORSM is seeing. And then I'm prolonging this experiment further in time to 2300 as a unforced pre-industrial control simulation, if you want. Yeah, then from this spin-up experiment, I started classic historical experiment 2014, and then run an SSP 585 to 2100. And then finally a prolongation of that forward until 2300. And this is using the scenario map prolongations that have been defined for CMIP6, where the CO2 emissions are reduced linearly starting 2100. And all the other emissions are held constant at 2100 levels. And this gives you a radiative forcing that ramps up to above 12 watts per square meter by the end of 2300, stabilizing. And from simple climate model simulations, you can estimate that that should lead to a temperature change of 8 degrees. And yeah, now I'm showing some results for these experiments. In orange, I always have the historical experiment. In green, the SSP scenario out to 2100, and then in red, the prolongation. And you can see here the evolution of the Northern Hemisphere sea ice extent, which is already rapidly decreasing in the SSP projection to 2100. And in these further prolongations, also the maximum sea ice extent. So this is the maximum sea ice extent, and this is the minimum sea ice extent, both going down to 0 at the end. The Southern Hemisphere is a bit more stable, but is also heavily decreasing in these experiments. So you can see from this here that 2-meter air temperature is increasing by up to 10 degrees in these experiments, so which speaks for a slightly higher equilibrium climate sensitivity of NORSM. The sea surface salinity is first slightly decreasing, then intensely decreasing, initially due to changes in the hydrological cycle, but then also at some point due to freshwater fluxes from the ice sheet, as we will see. And the AMOC is more or less stable over the historical period, and then rapidly decreasing to by 75% over the first leg here until 2100, and then basically to complete shut-off by the end of this experiment. And this has important impact on the heat flux, the northward heat flux that is transported by this circulation, which is basically also going to zero by the end of this experiment. So I want to show some figures on the Greenland response, and I've separated this into the near term, let's say 2100 response, and then later 2300. Yeah, what you see here in the top figure is the surface mass balance over this experiment. So you see over the historical period, you basically have like a stable surface mass balance, and then by the end of the historical, the surface mass balance starts to decrease initially, but then is kind of stabilized again for at least the first half of the 21st century until it starts to really kick in the warming, and the surface mass balance decreases. And this is an important difference to experiments that you may have seen from CESM2, where this decrease in the surface mass balance comes much earlier and has also much larger magnitude. Yeah, I will try to explain that in a bit, but first have a look at the sea level contribution, which is the plot just below here. So as I said earlier, with this kind of slightly biased initial surface mass balance that we initialize the ice sheet to, I get like a historical mass loss of around 20 millimeter over this 150-year period, which is more or less in line with some reconstructions. But this is produced here by a trick, by initializing the ice sheet to a slightly biased SMB. Then around 1960-1990, where often the ice sheet is assumed to be in steady state, this is close to steady state. And then you can see here that the mass loss kind of starts to kick in in the beginning of the projection, but then it is kind of halted or is not really taking off until much later in the 21st century. And so what we get out of this model in sea level contribution is about 2 centimeters, whereas in CESM2 you got something like 10 centimeters over this period. And this can be explained to some extent by a cold bias in NOASM. So especially around the Greenland margins, this model is a bit cold biased, which means that it takes a while until the SMP really starts to decrease. There's also a feedback through this very strong MOC response, which may explain some of this muted response over the 21st century. And also NOASM has a very low transient climate sensitivity. So on the long term, so in equilibrium climate sensitivity, NOASM is comparable to CESM, but it has some interactions in the southern hemisphere convection that makes that the transient climate sensitivity is much lower. So this is visible in these experiments here. This is contrasted by the response to the year 2300, where the whole system really shifts into a completely different state. Here we see like a massive decrease in the surface mass balance forcing, and we get to a sea level contribution of nearly 1.5 meters by this end of the 23rd century. In that case, you get ablation also very high up on the ice sheet. You lose several hundreds to thousands of meters of ice at the margins, and the ice sheet sees a strong retreat. Yeah, with this, I want to come to some summary here. So what I've shown here are the first coupled climate Greenland ice sheet simulations with NOASM2. Our initialization approach is to work around some of the climate biases that we're struggling with. We see a muted response of the Greenland ice sheet over the 21st century that I tried to explain by some of the characteristics of the NOISM, and then a very strong response until 2300. And the next steps will be to compare the standard NOISM experiments without the Greenland coupling to analyze the effects of the ice sheet climate interactions. And for this, we need really an experiment, a control experiment with NOISM that goes out to 2300, which we don't have at this moment. Yes, with this, I want to thank you all for listening, and I want to especially thank the people in the Land Ice Working Group that have greatly helped me to get forward with this work and have worked on CSM and CESM to begin with. It's Bill, Gunther, Kate, Marcus, Miran, Michele, Leo, and Raymond. Thank you all. And all that I've forgotten. Yeah, thank you.
Thanks a lot, Heiko. Right on time. Before we move to our next speaker, I just want to remind the presenters that you have questions in the chat. So if you can answer them, that'd be great, as you see fit. Our next speaker is Tim van den Akker, who's going to talk to us a little bit about testing the irreversible basal friction law in this MIP6-like experiments. So Tim, the floor is yours. Tim, you're muted.
I was talking to you already. Like, are you? I can hear you. You are muted, but this. Can you see my presentation?
Yes. You did good.
Great. Then we're going to start. So thanks, Gunther. My name is Tim. I'm a Dutch PhD student from the University of Utrecht, and especially from the IMAU, the Climate Physics Department. And for this project that I'm going to talk about, which will be about testing of the Zoot-Iverson law in ISMIP6-like experiments. So this fits nicely with Sarah's talk she just gave. I've been working together with Bill and Gunther and Willem-Jan van den Berg and Roderick van der Wal from here, from Utrecht University. So it should move to the next slide now, and it does, so that's great. So just to recap a little bit, so I will be talking about the mechanical boundary, or the mechanical boundary condition at the base of the glacier. So exactly where the glacier hits the base, the bedrock, we need to impose some kind of physical formulas to impose our mechanical boundary conditions, which we call basal friction. And I just took a random image here to show you like what it's roughly like, but exactly, especially the high surface velocity and the low basal friction proves to be important, and the low surface velocity and the high basal friction. I mean, it kind of makes sense, right? If you have low friction, you have high velocities, and of course the other way around. So what we'll be talking today about is a bit of my work lately on the Zoot-Iverson law and a little bit of a comparison with the pseudoplastic law. So exactly what Sarah has just been doing, but now for Antarctica. So on top here, you see the Zoot-Iverson law, and I'm going to quickly walk you through it. You see there is a CC, which I call Coulomb C, an N, which is the effective pressure, and there is some term with some velocities in there, and an exponent. So that's basically usually what the basal friction law is. It relates velocities, basal velocities of your glacier to a basal friction. And this is the new one, and it's actually a pretty cool basal friction law in the sense that it's determined experimentally. So Luc Zoet, I think he in his laboratory took slabs of ice and pieces of rock and sand, and he pushed it over it and to see like, and they derived this kind of friction law from it. So the earlier friction law in CESM, which is the pseudoplastic law, is written over here. It's the lower one. It looks the same, at least the beginning, except that the last part is slightly different compared to the Zoot-Iverson law. And those last two parts, the speed fractions, I have plotted over here to the right. And you can see, for example, that the Zoot-Iverson law, if you increase basal velocities, goes to 1. And the pseudoplastic law goes to, well, whatever, infinity. It goes up, it keeps on going up. Which proves to be important as well, because we are not using a friction angle in the ISMIP experiments, like Sarah did, for example, but we are inverting for this parameter. So we take this parameter, say that it's not very well constrained, and then we invert for it to get to our observed thicknesses and velocities. So that also means, for example, that if you're using the pseudoplastic law, you get a different inverted Coulomb C, for example, than when you're using the Zoot-Iverson law. That's kind of important to realize when you're doing perturbation experiments. So we're inverting in this kind of way, which is an equation with three important terms. The first one here is to do with thickness difference between the observed values and the modeled values, and it basically follows the rationale. If your modeled ice is too thick, you need a larger ice flux to get rid of it, so you need less basal friction. So you need a lower Coulomb C. The second term is here to prevent the thickness changes to be too large, so to prevent oscillations from happening in the modeled thickness. And the third term is the same as the first term, but then with surface velocities, following actually the opposite rationale. If your surface velocities are too high, so your ice is flowing too fast, you need more basal friction, so a higher Coulomb C. I also included the Zwally basins here to just illustrate a little bit what we're doing with floating ice now. So this is actually also only the grounded part that I see now, but anyway, you can imagine that there are ice shelves here around Antarctica, and we divide them into basins, into ocean basins, and we say every ocean basin gets a thickness target, and we can adjust either our ocean temperature or our viscosity of the ice shelves to get our ice shelves into the position we want them to. So I'm going to show you some Zoot-Iverson results that were observed, that were obtained lately with the CESM. This is a 4-kilometer resolution run with Zoot-Iverson for the Amundsen Sea region, and the color shows the thickness difference between the model and the observed from bed machine 2, as well as some other features such as and by the way, the top blue box here is the Pine Island Glacier, and this lower box here is the Thwaites Glacier. And this is just a general model run to show you, like, okay, it actually works and it kind of does what we want to. Because first we focus on the Pine Island Glacier, and we see that the grounded line of the model, so the yellow line, is a bit further advanced compared to the green observed grounding line. And this is actually what we want to do, because over the past weeks to months, we started to realize, like, okay, if we tune it towards a present day condition, Antarctica is probably unstable. That means that if we let it loose without any forcing, then it will give us model drift, and we don't want it, because we are in the future willing to do perturbation experiments. So we want to be in a more stable position. So we advance the calving front a little bit, and the Pine Island Glacier grounding line actually, yeah, it kind of moves with it. It's nice. But the Thwaites Glacier grounding line does not do that yet. So it does not follow the same pattern as, for example, of the Pine Island Glacier. So that's something I'm still wondering what's happening over there. What has improved, for example, with increasing the resolution from 8 to 4 kilometers, is that the Thwaites tongue is now grounded in 2 spots. So in 2 different spots here, on the eastern side and on the western side. Earlier, it was only like one big blob where the tongue of Thwaites was grounded, and the differences were, well, like our model Thwaites tongue was very uniform, and that was not actually shown in the observations. So that is something on the Amundsen Sea region where I'm still focused on. A bigger problem occurs here. This is the Field-Neuronne shelf, and what you can immediately see down here is that the modeled grounding line has retreated a lot compared to the observed grounding line, while in other areas of the Field-Neuronne it actually does the same thing as it does for the Pine Island Glacier. So what this is basically there is an ice rise over here called the Bungenstock ice rise, and as soon as CESM shifts the modeled grounding line away from it, it will kind of collapse, as you can see over here. Like white values are below 500 meter thickness differences. Bill has done some testing with the ocean basins and the velocity or the viscosity inversion, and the results look promising. It does not collapse in the same way, but we're still not completely confident that we know what's going on, or we know, I mean, it collapses, so we know what's going on, but we do not know yet what to tune or what to turn to get it actually at the right position. So what have I been doing as well is, so now what, yeah, we can, this is a DHDT data set from Smith et al. In 2020. And what I'm trying as of right now is to see if we can use this DHDT dataset, so the thickness change of the ice, to get one, Antarctica into a more stable position, two, to get it into or let it move to the present days of DHCT as we want it, and 3 to test it through to see if we can get through the current day position with the right DHCT. Now, what I'm doing right now is I'm putting this DHCT on top of my SMB, so to tune it towards a slightly higher ice thickness in areas where there is thinning observed. And then exactly at the moment that I want the model to start, I remove the DHCT again, so that it immediately from the mass balance equation produces the right DHCT values that I want. This is, by the way, still a work in progress because I'm still struggling with Ben Smith from the author of the paper about the data and the figures and the right units that I'm using, but that is the direction that I'm going into right now. That was it, actually. Thanks for your attention.
Thanks a lot, Tim. Oh, you make us be ahead of our schedule. Great. Doesn't happen very often.
But we skipped on that.
So again, yeah, there's some questions in the chat, some good discussion. Keep it coming. And so we're going to move to our last but not least talk of the morning with Mira Biadal, who's going to tell us more about what we've been doing with the waste metallic ice sheets. And she's going to tell us about under what condition does the waste collapse, and some evaluation with using CSM2. So yeah, the floor is yours.
Okay, thanks. Can you see my screen there?
Yes, looks
Okay,
great.
great. Actually, let me move you guys over so you're not on your screen there. Oops, just 1 second. Okay. All right. Yeah, thanks for having me here. My name is Mira. I'm a postdoc at the University of Washington. And today I want to talk about a new NSF project that we just started on, and it's a collaborative effort between University of Washington, NCAR, Brookhaven National Lab, and Washington Sea Grant. And the project is, the overarching question of the project is, under what conditions does West Antarctic ice sheet collapse? And today I'm just going to talk about some preliminary results where we evaluate the Southern Ocean response during the last interglacial in some CESM2 runs. So quickly, some background. The last interglacial, also called the Eemian, lasted from roughly 130,000 to 115,000 years ago. And the climate during this period was roughly 1 degree warmer than the pre-industrial, and the peak mean global SSTs were similar to that of the 1995 to 2014 mean. Cores from Antarctica suggest that the temperatures were roughly 2 degrees warmer there, while temperatures in Greenland were possibly more than 4 degrees warmer than the pre-industrial. Importantly, there is evidence that global mean sea level was at least 4 meters and possibly up to 6 to 9 meters higher than present. And estimates suggest that Greenland contributed about 2 to 5 meters of this to the sea level, which then suggests that there must have been a fairly large contribution from Antarctica. And therefore, it's believed that waste likely collapsed to some extent during this period. So overall, our project aims to understand the conditions for waste collapse, both during the last interglacial, and we also plan to apply what we learned from the last interglacial simulations to some future scenarios as well. And I'm going to get into some more details on our planned simulations and some preliminary results soon. But first, I just want to discuss some of the mechanisms that are believed to be at play here. So the predominant thinking is that the Antarctic mass loss results from a reduction or collapse in the AMOC. So on the right here, you see a conceptual diagram showing what is thought to have happened at the end of the penultimate glaciation. So there's a large freshwater anomaly that occurs in the North Atlantic as a result of fast melting ice sheets in the Northern Hemisphere. And this freshwater is dumped, when this freshwater dumping is referred to as a Heinrich event. And in particular, the one that occurred during the last interglacial is called the Heinrich 11 event. So when I refer to H11, this is the freshwater dumping that I'm referring to. So when this freshwater is dumped into the North Atlantic, the deep water formation in the North Atlantic is suppressed, and there's a general cooling in the north, and this allows heat to accumulate in the Southern Ocean. So this anti-phasing of Greenland and Antarctic temperature is referred to as the bipolar seesaw. And there's evidence in the cores from both hemispheres that this anti-phasing does exist in the past. So we see that here. These show the temperature anomalies with respect to the last millennium for Greenland on the top panel and Antarctica in the bottom panel. And if you take a look at the gray shaded areas, these correspond to periods of cold temperatures in Greenland. And if you follow that down to Antarctica, you can see that while Greenland is in a cold period, the Antarctic is actually in a period of warming. So there seems to be a lag there as well. So this is the bipolar seesaw, and this is evident in these proxy records. And I want to briefly mention here that the default train of thought in the community is that H11 is a forcing on the climate, leading to a chain of events, including ice loss from Antarctica. But this isn't still fully understood. And another hypothesis might be that the H11 happened because of climatic forcing. So in other words, the AMOC reduction and H11 timing event timing is not super constrained yet. So anyway, let's talk about our project and the specific questions we are seeking to answer. So the first big question is, what if waste collapse during the last interglacial can be explained with only a modest amount of ocean warming? So for example, could you still trigger a marine ice sheet instability without any fast like marine ice cliff instability, Mickey style mechanisms? So this would be our working null hypothesis. And even though today's talk will I'm only going to focus on the paleo side of this work, I do want to highlight briefly that this project also involves work on future climate. So in this portion of the project, we will ask what level of future forcing is sufficient to drive waste collapse? And once waste collapse is triggered, how quickly will the ice sheet lose mass and raise sea level? And I have to say, I'm personally really excited to work on this particular set of questions because we have partnered with folks at Washington Sea Grant who are coastal hazard and sea level experts, and they have the expertise in digesting scientific results on sea level rise that the science part of the team may not have. And they regularly engage with public agencies and local communities. So the hope is that this project will ultimately feed into some of their comprehensive climate change vulnerability assessments. So now I'll get into the simulations we have planned to address these questions. And again, I just want to say that we're just going to focus on the paleo portion of this work for this talk. So we have plans to use CESM at FV2 resolution, 2-degree resolution, CISM standalone, and CESM coupled Antarctic. So CESM coupled with an evolving Antarctic ice sheet. The first set of paleo runs we have planned actually are complete. So the CESM ones anyway. So we have, they involve transient CESM runs during the last interglacial, one with and one without an H11 freshwater forcing. And these will act as boundary conditions for a large CISM ensemble in which we will be able to explore the CISM parameter space and explore climate boundary conditions. Next, we will follow a similar process, but this time we will use a coupled CSM with an evolving Antarctic ice sheet. And we will once again do this for the last interglacial conditions and LIG conditions plus a freshwater forcing. So for each of these coupled CSM-CISM runs, we will also explore high and low thermal forcing sensitivities in the ice sheet. And once again, we will use this output as boundary conditions to another CISM ensemble. And this will help us further refine the ice sheet parameter space that leads to waste collapse. So overall, with this collection of runs, we'll be able to explore a number of under-constrained issues like the large-scale ocean boundary conditions, the methods of heat delivery to the ice shelves. For example, we plan to explore methods ranging from simple melt rate parameterizations to reduced order ocean models and variations in ice shelf physics. So today I'm going to focus on the first set of paleo runs and go through some of the early results from these last interglacial simulations. So very quickly, the 127 Ka runs are set up with orbital parameters, vegetation, greenhouse gases that are all prescribed to LIG levels. So on the right here, you see the solar insolation anomaly during the 127 Ka run with respect to the pre-industrial. And you can see there's a large positive Northern Hemisphere summer insolation anomaly here, which is part of why global temperatures during this time were warmer. All the other forcings, such as the solar constant, ozone, volcanic aerosols, topography, and ice sheet configuration remain the same as in the pre-industrial. So the CSM control run, I call it 127 Ka control, is run for 1,000 years. And then we also run an identical simulation in all regards, except for the addition of 0.2 sphere drops of freshwater forcing in the North Atlantic. We call that the 127 Ka H11. And this is, the forcing is turned on instantaneously and kept at that level for full 4,000 years. And that's in an effort to simulate the H11 event during this period. Okay, so what happens in these runs? To start, let's look at the surface ocean temperatures. So each panel is a 50-year mean of the anomaly of the H11 run as compared to the 127 control. And I'm just showing some snapshots in time to give you a sense of what's happening. First, at the beginning, the left panel shows the beginning of the H11 run. The middle panel shows about 250 years in, and the right panel shows about 500 years into the run. And we can see a definite bipolar response due to the H11 forcing, where the northward transport of ocean heat is suppressed due to the H11 forcing, causing the northern hemisphere oceans to cool and the southern hemisphere oceans to accumulate heat. Now let's take a look at how the Atlantic meridional overturning circulation, or the AMOC, responds to this H11 forcing. These panels show decadal average slices of AMOC circulation. And each panel has a y-axis of depth, and the top being the surface, and it goes to down to about 5 kilometers. And the x-axis shows latitude centered on the equator. The red regions indicate clockwise circulation, and blue indicates counterclockwise circulation. So basically, you don't need to look for too much nuance here, but you can simply see that at the beginning of the run, there is a strong overturning circulation indicated by the dark red colors, and this diminishes with time and remains suppressed over the course of the H11 simulation. Another way to get an idea of how the overturning strength is affected by the H11 event is by searching for the maximum value in this region. So we do this looking north of 28 degrees north and below 500 meters depth. And this will give us a sense of how this cell strength evolves over time. So I'm showing here the strength of that cell in 3 different runs. On the left panel is the H11 run, the middle panel is the 127 control, and the right shows the pre-industrial control. And the MOC is generally broken up into different components. The Eulerian mean is just the transport by the mean velocity fields, and this is shown with the red curves. The eddy-induced indicates the transport done by eddies, which is shown in blue, and the total is just the sum of those two that I show in green. So what we see is that in the North Atlantic during the H11 run, there's a sudden and very sustained reduction of the strength of this cell in the North Atlantic as compared to the control runs. So indeed, we are finding that the H11 event suppresses AMOC circulation. So next, I'm going to walk you through some mean ocean temperatures for different regions. First, the Southern Ocean region, which we say is everything south of this black line here. And the curves on the left show the ocean temperatures at different depths, starting from the surface in blue, that's at I think 500 centimeters, and moving down to about 500 meters in depth. So the short runs are the 127 control, and the long curves that last 4,000 years are the H11 runs. So we find that the temperature is warm on average in the Southern Ocean down through the upper 500 meters of the column. And next, if we look just at the Amundsen Sea, which you can see indicated by this blue region, we see the same story. The upper 500 meters of the Amundsen Sea warms on average as a result of the H11 forcing. So here's where things take an unexpected turn. We take a look at the ocean waters that are more important in terms of what the actual Antarctic ice sheet will interact with. So I call this the tight Southern Ocean, which is indicated in yellow. So the plot on the left is showing the average temperatures with depth for anything south of this line. And what we see is that the 2 upper levels, so 500 centimeters and about 100 meters depth, there's an increase in temperature in the H11 run. And I believe this is likely linked to the sea ice response. However, below this, ocean temperatures actually experience a cooling that lasts almost a millennium. And that's followed by a very slow rebound in temperatures. So by the end of our 4,000-year run, the temperatures at this depth range never fully recover at these to the original level. And this is super important because ice shelves around the Antarctic periphery are exposed to ocean waters at about 500 meters of depth. And these are the depths which determine the melt rates. So I want to point out that to my knowledge, this cooling at depth has not been seen or simply not explored in the literature yet. And it's important because even if the cooling is minimal, like it is here, it may still be relevant for the ice shelves. So we've taken some preliminary steps at trying to figure out why this is happening. So first, and we find that the westerlies that circulate around Antarctica actually shift poleward and show some strengthening. So I'm showing the difference between the H11 run here and the 127 control run averaged over time. So here we just see there's a poleward migration of the westerly winds in this anomaly plot. And in order to understand the effect that these winds would have on the ocean, you need to look at the wind stress curl. So here I'm showing you a plot of wind stress curl anomaly in the H11 run compared to the 127 control. And what you need to know here is that areas of negative curl anomalies imply a positive Ekman upwelling. So in other words, blue and purple areas we see in the Southern Ocean near the Antarctic ice sheet indicate that the surface waters will move northward due to Coriolis, and this will allow deep water to upwell. So at this point, we suspect that the initial cooling in the tight Southern Ocean at depth is a result of Ekman suction. And next, we want to try and understand how the temperatures at these depths begin to rebound. So in other words, what is the mechanism driving these temperatures back up again? So our suspicion is that this temperature rebound may have to do with eddy transport of heat across the Antarctic circumpolar current, this ACC, this sort of red zone of circulation around Antarctica. So specifically, what if the heat during the H11 run is being stored north of the ACC, and then perhaps eddies are responsible for transporting heat south of the ACC? So I realize I'm running out of time, so I'm just going to say that we do have an early indication that this may be happening. So in the H11 run, so what we're looking at here is just the eddy-driven MOC strength in the deeper Southern Ocean. So these all have negative values, which indicate counterclockwise flow. So basically a bigger negative value implies a stronger eddy-driven flow. And so we see that in the H11 run in blue, the eddy-driven transport strengthens and remains stronger for the entirety of the run, in contrast to the two control runs. So at this point, we haven't deduced what is going on here, what the reasons for this is, and so that's still under investigation. But I do want to point out that this is actually consistent with work by Pedro et al., which is a lovely paper, who argues that the thermal reservoir during the Heinrich events is actually north of the ACC. And due to the difficulty of propagating anomalies across the ACC, that would take time. So they also showed that eddies were crucial for transporting heat south of the ACC. So in summary, our Heinrich simulation shows that there is a short-term cooling at depth near the Antarctic ice sheet, which was surprising to us, and that this is likely a result of wind-driven Ekman pumping. And these temperatures barely rebound to initial values even after 4,000 years. And we suspect that this long-term warming is facilitated by eddy transport of warmer waters that have accumulated north of the ACC and are eventually transported south closer to the Antarctic ice sheet. So that's it for me.
Thanks a lot, Nora, and thanks a lot for all of the speakers, the second session and the entire session of this working group. And please keep posting your question in the chat, and we will move on to our discussion. So Bill and Jan, I don't know how you'd like to work on this.
Excuse me. I think we'll just open the floor to questions from anyone about any of the talks we've had today.
So I don't know if I can do this, but I can do this, but I will. Tim had a question for Sarah in the chat that remained unanswered at this point that I can see.
She replied to me already personally.
Oh, okay. So. Never mind.
So I have a question that might be bringing together a lot of talks, and that's maybe particularly for Bill Lipscomb. Bill, how do you see the schedule for Antarctic CESM simulations and the interactions with MOM6? Are we talking next year? Is it 2 years? Is it 3 years? And what can we do in between that, as a community to help this moving forward, or do science that is, along the lines of what Tessa is doing, what Mira is doing, what Tim is doing. I mean, there's a lot of relevance to this from many aspects, but maybe I'm personally interested in knowing what on the NCAR side, what the planning is.
That's a great question. Are you thinking mainly about the coupled simulations, or
yes?
Or well, we have this great new tool where we can run Antarctica coupled to CESM now, but it still needs a lot of testing. So I would think for the next 6 months or so, we're going to be putting in some of the last coupling mechanisms in terms of MOM6, experimenting with having MOM6 compute subsurface melt rates versus having those computed in CISM, given MOM temperature and salinity, that sort of thing. So I would I would guess that we'll need most of the rest of this year to give things a run and put in some remaining hooks and work the bugs out. After that, we have this this great tool that we haven't had before, and we don't have an organized plan yet for who's going to do which experiments. And I think that's something that we should talk about. One of the challenges, obviously, is how do you get financial support to run with the new tool? I mean, you need to demonstrate the tool is working before you're likely to get the support. But then once the tool is working, there's a lag in time that it takes to do the proposals and get proposals accepted. Do you have thoughts about that yourself?
I agree. I think that's why it's important to have meetings like this where we report on progress so people can know what the status is. So I think it's going to be important to keep the community updated on the progress, because I know that there's a lot of interest in this application from various sides. So yeah, that's all I can say, and I agree with you. It's hard to write a proposal or get a proposal funded mentioning something that hasn't really been around that long or is just new. So I think we need to be a little bit patient, but I think also, and that's the other side of my question, is that we can do a lot of stuff before that happens that is also relevant. So yeah.
I'll just add a couple of things. One is I think it would be, those of us at NCAR can try to have an update at the summer meeting on here's some preliminary tests we've run and here's what we think is actually working. And if you go check out this particular branch, this is an experiment you can do yourself. Also, I think Mira's talk was a great example of work we can already do with POP. And she wasn't showing results with any ice sheet results yet, but we do plan to force the ice sheet with POP temperatures and salinities. And so that's a way we can get a jump on things and demonstrate things with POP. And then as MOM6 comes online, we know that these things will technically work. They'll work just differently with the new ocean model.
And so do you envisage, let's say as the ultimate dream, to have CSM3 run with both ice sheets coupled to the climate at the same time?
Yes, that would be the dream.
Okay.
I don't know if it's the ultimate dream, because ultimately we want to have interactive solid earth and sea level and the ocean geoid adjusting and things like that. And I think that's probably more a target for CESM4 or some future version. But for CSM3, I think we can have with a few simplifications, I think we can have both ice sheets coupled with ocean as well as atmosphere coupling.
I have a question for everybody here. After Tessa's talk, I forgot if it was Dave America, I was saying that POP is limited in the type of analysis we can do because of its nature. And I'll say, once CSM3 is up and running, does everybody agree that POP can be retired completely and that we're done with the type of science we could have learned from it? And I do not know the answer to this question. I'm wondering at this point.
I think we're a long way from retiring POP. I've heard from Keith that one of the constraints is the BGC, because they're working very hard to get the BGC working in MOM. But I think that there's still going to be many years of having to do POP BGC experiments. So.
I guess BGC set aside, in order to work with science on ice sheet and ocean coupling, and sea ice for that matter.
I think that's the way we should go, but again, I think, there's POP still going to be there, still going to be available. And I bet you there's still going to be groups that are going to still want it. So.
I don't know, my impression is it's going to depend a bit on how solutions look with MOM. So
exactly, yeah. I mean, we're still working on that coupling with MOM, and that's still gonna take some more time. So
we see where we are a year from now. I don't think we can definitively say when POP will be retired, is my impression. I'm sure the oceanographers don't want to maintain 2 ocean models within CESM. So I think I agree with Dave that it's the ultimate goal to move away from POP, but I just don't know how long that's going to take.
Bill?
On a different subject, Heiko, I was really interested in your results, and in particular, how you showed that you had a very modest response in terms of sea level rise from Greenland until 2100, and then a very fast response after. So it seems like the behavior, maybe this shouldn't be surprising, but the behavior we're seeing from Greenland is in coupled models is looking very rich as we see more models, NOR-ESM and CSM, as well as UK ESM. And I'm wondering, what do you see going forward as a good way to try to figure out what, not simply which model is right, but what are the possibilities that look most realistic as opposed to others that may be more model artifacts?
Yeah, good point. I mean, I have to say I was really surprised. I was almost shocked because I had just assumed that NOR-ESM would behave very similar to CSM, just because, many of the components are the same. And I mean, this difference in transient climate sensitivity is well documented in at least one paper now. So I think that's, as the more models you look at, the broader you will see responses going forward. But I mean, so I think it would be interesting to really work towards including more models in something like a MIP, like getting back to the original idea to really have experiments that everybody does. And but there's also then the question, I think the difference in the response, maybe I haven't mentioned that, is also how the ice sheet looks like, because I have this really small ice sheet, let's say, compared to what you have in CESM. And that, of course, makes that a much smaller area can possibly respond to changes. And so that may also have a huge impact on how the ice sheet can respond. And with that, it's a combination of different things. So, and always the question, then do you learn most from people doing all the different things, or do you learn most of, pushing people to do more similar things?
What do you think? How would you answer that?
Well, I mean, it depends on what everyone wants to do, right? So generally, the more people look at more different things, that might be better. I'm particularly interested in all these trends towards high resolution and glacier modeling and so forth. So I think we should try different things. I'm just not sure I want to do this all myself or with just our group, because that's too slow.
And Heiko, I'll just draw your attention to a request from Adam Harrington in the chat.
Yeah, I've seen that. I'll post that in a second. I didn't find the DOI. I just had the title.
Thank you, Heiko. Are there any questions about the or comments about the glacier talks we had earlier in the morning? Well, I'm excited about looking at glacier evolution. One technical point I'll mention is that we do have the ability in CESM to, if we have a grid that, let's say, is 10% covered by glaciers and the rest of it is ice-free, we can input a mask that says where we expect ice to be and not be, and use that mask to throw out the parts of the domain that we're not interested in spending computer time. So that's one of the key things that will allow us to model large regions. I'll just mention that if the dream, at least my dream, is to model all the Earth's land ice, including the glaciers, one of the challenges we'll face is when we get to regions that have a lot of marine terminating ice, Alaska, the high Arctic. The land terminating glaciers are easier, and we haven't given much thought yet to how we'll handle, say, an ice cap.
So we have a similar problem actually with the representation of data, that so far a lot of the community is limited by these masks that exist. So there are land masks for making land surface height, and especially for sea ice, it's bad that there are ocean masks and sea ice masks. And then suppose a glacier retreats, then of course the sea ice will advance against the glacier. But those problems are handled by a totally different part of the community. And so even if the people want to talk, then the masks are making all the science trip up. So we're working towards having something that automatically adapts across all these masked boundaries, because that's where the change is, right? So I'm just saying, I do know perhaps how to do this with data, but it would be cool to figure out where the real advantages lie for the modeling community from some of you who know particularly where we are hampered by these masks.
Heiko, your hand's up.
Yeah, along those lines, I mean, what we did in this MIP 6 is that we kind of got together with the Glacier MIP people to kind of negotiate which part of the domain we're taking into account. But this also showed that we're kind of playing on different levels, because while the ice sheet is kind of really a 2D entity, the glaciers, as has been pointed out before, are treated as kind of single entities. So they don't really have, well, somehow they have a spatial extent, but the way they are modeled, they're basically just picking individual models. Individual glaciers. So that's a challenge, I think. Yeah, but I also had a thought about this kind of widely distributed array of glaciers that you are simulating. With the new coupling framework, does it make sense to split that up into smaller regions? Does that help you to, yeah, to kind of distribute it, or where's the breaking point where you don't want to split in individual glaciers?
Are you thinking about within a coupled framework?
Yeah, like with the CESM.
Right.
CESM.
Well, I guess the first question would be whether you need a couple of framework for this. Do you think, for example, that changes in high mountain Asia glaciers will modify the climate in a way that will affect the further retreat of the glaciers? My guess would be a small effect, but perhaps it's still worth doing. And in that case, you would simply add another CESM region to CESM in addition to or in place of Greenland or Antarctica. In theory, we could do that for every RGI region. And then it becomes a bit arbitrary. How do you, the RGI maps might not be ideal. For example, there's this huge tropical region and you'd probably want to separate that into smaller regions. Not something we've given too much thought to. We did think about whether the high mountain Asia should be 3 regions or just 1, since in RGI it's 3 different regions. And we decided it's cleaner just to have it all as 1 region. But for the Arctic, maybe you just want to have an Arctic CESM grid that covers all of Greenland and all the glaciers, and just judiciously throw out all the regions where that aren't going to be glaciated. I had a question for Zhang Zhu. Zhang, are you listening right now?
Yes.
Oh, thanks. So one thing that came up yesterday was we had a scientist saying, I would love to use CESM2 for Arctic simulations, but it's too sensitive. And that scientist was saying, so I'm just going to keep on using CESM1 for a while. And we don't want to support CESM1 indefinitely, I don't think. And you've done, I think, more work than anybody in understanding the sensitivity of CESM2 and making changes that make it more appropriate for cold climate simulations. Do you see do you think it would be useful or possible to put forward a workhorse 1 degree version of CESM2 that's paleo calibrated or tuned so as to be less sensitive?
Yeah, I think it will be challenging to do for the 1 degree because it runs slow and it's very expensive. And the cloud-related processes are difficult to diagnose and to make sense. So I think that would be great if we have a higher, say, 1 degree resolution, but it's really difficult to do. Just we have some preliminary results looking at the 2 degree version of the model the paleo group have developed to use that to simulate the warm climate of the early Eocene. We have some unexpected results. So that has something to do with the state dependence of the cloud feedback. And then we are trying to figure that out. So I think in summary, it's challenging to do, and but we are working on that. So the goal is firstly, if we can have a good 2 degree version of the model that simulates both the cold climate, last glacial maximum, and the warm climate, early Eocene, that should be a very, very good starting point for us to looking at the 1 degree version of the model. But it will take a long time, I think.
Do you think it's worth doing that with CESM2 or just move on to CESM3?
I think it's really needed. We need a group discussion between, say, the paleo and the other working groups, including the land ice, sea ice, and the atmosphere modeling group, because sometimes, say, if the fixes we are trying to implement, if that changes the present day climate, say, make the clouds worse when compared with satellite observation, then we need to have some discussion with the model developers about the best way to move forward. because the model is not only used to simulate those extreme climate, they're also used to simulate the present day climate, the near future.
Adam, do you have thoughts on this?
A little bit, but I don't want to just, I guess I want to just double check with Jiang. This paleo calibrated version is for the finite volume 2 degree die core. And, you know, I think that is a good solution to Bill, who was bringing up the point that they don't want to run CSM2, they could just run finite volume 2 degree paleo calibrated. And the main issue with getting a finite volume 1 degree going is we've pretty much identified the cause of the extreme climate sensitivity as relating to how this ice nucleation is handled in the microphysics. And so my understanding, Gianna, is we have sort of several fixes for this, but to go ahead and just put it into the finite volume 1 degree model, the TOA might just be would be out of balance and would require allocating resources to tuning that up. That's the issue, right?
Yeah.
And so then I just want to bring up what Bill said going into CSM3. You know, so we're working on improving bringing this microphysics into a new version of the microphysics for what we're calling CAM7 development. I suspect that within about 9 months, 6 to 9 months, we will have a version on the trunk that has a realistic TOA balance with a more sensible climate sensitivity. So that's what I would suggest. Those who don't want to use CSM2 because it's too sensitive, use Jiang's paleo calibrated version. If you don't want to use finite volume 2 degree, then you're going to have to wait, you know, till the end of this year when us CAM folks have tuned up the new version.
Thanks, Adam. I agree. It's an issue. We don't have resources to tune and fix everything. We've got about 10 minutes before the hour, but we don't have to go all the way till noon. Are there any other questions or thoughts people want to bring up? Anything people would like to see discussed or at the summer meeting or happen before the summer meeting? If not, I just want to thank everybody for attending. Thank Elizabeth again for organizing and making sure everything runs smoothly. And for me, it's always fascinating to see a wider and richer mix of science and participation from around the world and other modeling communities every time we meet. So it's just really encouraging to see all the progress, all the connections between land ice and paleo and polar climate and other working groups. And I hope to see many of you again in person soon. I don't know if we'll be there yet in June, but hopefully not too long after that. So thanks again, everybody. We'll see you around.
Thank you, everybody.
Thank you for organizing. See you.